This year, millions of Audi Q3s were built with robotic precision inside the most advanced automotive factories in the world. From molten metal frames to laser-welded panels and hand-fitted interiors, every stage blends cutting-edge automation with meticulous craftsmanship. Today, we go inside the production line to see how the 2026 Audi Q3 is designed and assembled to deliver performance and unmistakable German engineering. The manufacturing of each Audi Q3 begins with the formation of its steel and aluminum body structure. Massive coils of high-strength steel arrive in large rolls, weighing several tons each. These coils are loaded onto automated decoilers that unroll them and feed the sheets into precision stamping presses. Each press stands several meters tall, equipped with dies that shape the panels through thousands of tons of force. The press line operates sequentially, first drawing the sheet into rough form, then trimming, flanging, and piercing it to exact dimensions. The stamping process produces components like the doors, roof panels, side frames, and floor assemblies, each piece emerging with clean edges and uniform contours. After pressing, robotic conveyors transfer the panels to inspection stations. Optical scanners project structured light patterns over the surface to detect any minor distortions or wrinkles in the metal. Panels that meet tolerance move into the body shop, where automated guided vehicles position them precisely for assembly. The body shop floor is dominated by robotic arms mounted on tracks. Each one executes programmed sequences of spot welds, reaching with synchronized precision. Sparks flash rhythmically as up to 5,000 welds are applied to form the shell of a single Q3. The sound is constant, a rapid sequence of metallic pops and short bursts of compressed air as clamps secure each joint. The underbody assembly begins on a fixture that locks the floor pan in place. Side panels are positioned next, followed by the roof and rear section. Laser measuring systems continuously check alignment to within fractions of a millimeter. Once the welds are complete, the body shell, now called the body in white, moves by overhead conveyor to the next section. Here, lightweight aluminum parts, such as hood and tailgate panels, are joined to the steel structure using adhesive bonding and self-piercing rivets. Robots apply structural adhesive beads in continuous lines along predefined paths before pressing the parts together with uniform pressure. The curing of the adhesive occurs later in the paint shop's high-temperature ovens. The next phase is surface preparation. The bare metal body enters a cleaning tunnel where rotating brushes and high-pressure sprays remove all residues of oil and dust. After cleaning, it passes through a zinc phosphate bath. This chemical treatment creates a fine crystalline layer that improves corrosion resistance and adhesion for subsequent coatings. The body is then fully immersed in an electrocoat tank. Electrical current flows through the liquid coating and the body structure, attracting the charged paint particles uniformly to every metal surface, including internal cavities. The body is then baked in an oven where the coating hardens into a thin, durable primer layer. When cooled, the body enters the sealing line. Robots apply bead lines of PVC sealant along all joints, seams, and edges to ensure total watertightness. The sealant is smoothed by rotating brushes and shaped nozzles for a clean appearance. Next comes the paint application area, enclosed within a dust-free cleanroom environment. Each body is statically charged, and atomizing robots spray the paint in fine, electrostatically charged droplets. The color layer is applied in multiple passes, followed by a clear coat for gloss and protection. The paint booths are ventilated with laminar airflow, carrying overspray away to maintain surface purity. Each painted body then moves through a multi-stage oven where heat polymerizes the layers into a hard, glass-like finish. As the body emerges, cooling fans bring it back to ambient temperature. Parallel to body production, the powertrain components are being assembled. The Q3's engine block begins as a cast aluminum alloy. Molten metal is poured into precision dies under high pressure, forming the complex structure of the block with integrated coolant channels and bearing seats. After solidification, automated saws remove excess material from the casting gates, and the blocks enter the machining line. Multi-axis CNC machines bore the cylinders, drill oil passages, and mill the deck surface to exact tolerances. Robotic arms rotate the blocks between stations, while measuring probes verify alignment of the crankshaft journals and cylinder bores. The interior surfaces are honed to achieve a fine crosshatch pattern for optimal piston movement. The crankshaft is forged from steel billets. Each billet is heated to a bright orange temperature before entering a multi-stage press line where dies shape the webs and journals with tremendous pressure. The forged piece is then cooled slowly and sent for machining. Computer-controlled grinders shape the bearing surfaces to micron-level accuracy, achieving a mirror finish. Each finished crankshaft is balanced automatically by high-speed sensors and corrective drilling systems that remove minuscule amounts of material. Pistons, connecting rods, and bearings are prepared in parallel. Robots assemble piston rings, insert wrist pins, and pre-lubricate components before the sub-assemblies converge on the engine line. The engine assembly line operates in a modular sequence. Blocks arrive on moving pallets that stop at each workstation for automated installation of components. The crankshaft is placed into position and secured with main bearing caps tightened by torque-controlled tools. Pistons and connecting rods are inserted into the cylinders by robotic grippers that align and slide them smoothly through guiding sleeves. Cylinder heads, previously machined and fitted with valves, camshafts, and timing components, are then lowered onto the block and bolted by synchronized electric drivers. Once assembled, the completed engine undergoes a leak test and a dynamic cold run, where electric motors spin it to check compression and resistance. Data from each test is recorded in the system for traceability. Simultaneously, transmission units are produced. Aluminum housings are cast and machined with similar precision. Internal gear sets, clutches, and shafts are assembled by automatic stations that align components with optical referencing. Final transmissions are filled with calibration oil and tested under simulated driving conditions using electric drive benches that monitor torque output and gear engagement smoothness. The engines and transmissions are then mated together into complete powertrain modules, ready for integration with the chassis. Seat frames, pre-assembled with side airbags, adjustment mechanisms, and upholstery covers, are delivered to the line on synchronized trolleys. Robotic grippers lift each seat and angle it through the door aperture before lowering it onto the floor rails. Electric drivers tighten the mounting bolts in a programmed sequence to ensure even torque distribution. Rear seats are positioned next, locking into brackets that are welded directly to the body structure. The interior begins to take shape as the carpeting, insulation layers, and headliner are installed. Automated dispensers roll the carpet into position, and vacuum-guided applicators press it into every contour, including the footwells and tunnel. The headliner is lifted upward by suction cups and fixed with clips along the roof edge, concealing wiring channels for lighting and sensors. Door modules are prepared in parallel on a separate sub-assembly line. Each door shell, already painted, arrives with its inner panel exposed. Automated stations install window regulators, locking mechanisms, speakers, and seals. The glass is robotically inserted and bonded with precision-controlled adhesive beads, ensuring airtight closure. The door trim panels, consisting of molded composites with integrated switches and handles, are then pressed into place by pneumatic actuators. Fully assembled doors are conveyed to the main line, where articulated robots lift them and align them to the body hinges. Laser sensors verify the alignment gaps and flushness before the hinge bolts are tightened. The fit is measured to tenths of a millimeter for uniform spacing along the entire side of the car. Moving further down the line, glazing robots install the windshield and rear window. Each piece of glass is handled by vacuum pads and oriented with exact angular positioning. The bonding adhesive is applied in a continuous bead that is metered by flow control systems. Once the glass is pressed into place, ultraviolet lamps initiate the curing process to secure an immediate initial bond. Side mirrors, wiper arms, and the roof antenna module are attached next. The exterior lighting systems follow. Headlamp clusters, taillights, and indicators are positioned by robotic arms that verify orientation through embedded vision sensors. Each light unit is tested electrically as soon as it is connected, ensuring perfect function before the vehicle continues. The next phase involves fluid filling and system calibration. Automatic filling stations connect flexible couplings to designated ports under the hood and chassis. Coolant, brake fluid, power steering fluid, and air conditioning refrigerant are dispensed with volumetric precision. Each circuit is then pressure tested by integrated sensors to confirm leak-free sealing. The fuel system is filled with a small amount of test fuel for functional checks. The onboard control units, already preloaded with initial software, are powered for the first time. Electronic control networks within the car synchronize as systems awaken, exchanging diagnostic signals over high-speed communication buses. The line monitors confirm successful handshake between modules such as engine control, braking, and infotainment. Tire and wheel assembly takes place on another automated station. Alloy wheels are fitted with tires by robotic tire mounting machines that use hydraulic rollers to slip the tire beads perfectly over the rims without deforming them. Each wheel is balanced automatically using precision sensors that measure weight distribution. Small adhesive counterweights are added to achieve zero imbalance. The completed wheel assemblies are transported to the vehicle, where a robotic manipulator aligns each wheel with its hub and fastens the bolts in a star pattern using controlled torque drivers. The car now rests on its wheels for the first time, supported by a conveyor platform that rolls it to the dynamic calibration area. In the alignment zone, laser systems check the vehicle's suspension geometry. The sensors project grids across the wheels and body to detect the exact position of each corner. Automated adjustments correct any deviation by turning the control arms or adjusting tie rods through servo motor-driven tools. Headlight aimers adjust the beam patterns to specified heights and angles based on optical targets placed ahead of the car. Cameras embedded in the roof and bumpers are calibrated by projecting specific test patterns onto surrounding panels, aligning the onboard assistance systems for accurate spatial perception. The steering angle sensor, traction control, and adaptive suspension systems are all initialized here. Next comes the powertrain wake-up sequence. The vehicle is moved onto a rolling test bench equipped with dynamometers for all four wheels. The engine is started for the first time. Sensors measure torque, emissions, and noise, while electronic control units refine their calibration parameters. Each gear is engaged and tested under load conditions that simulate real driving scenarios. The results are compared against standard values stored in the system database. If the data matches expected performance, the car advances to the final inspection line. Exhaust extraction ducts and soundproof walls surround the test benches, containing the controlled bursts of sound from the engines as dozens of vehicles undergo testing simultaneously. Following mechanical validation, each car proceeds to a meticulous water tightness test. The vehicle enters a sealed chamber where hundreds of nozzles spray water at high pressure from every angle, simulating heavy rain. The chamber's sensors record any internal moisture detection through humidity probes placed inside the cabin. Once the test ends, the car passes through a drying tunnel, where heated air circulates through the body cavities and upholstery to remove residual moisture. The car then moves into the quality verification section, illuminated by bright white panels that reveal even the slightest surface imperfection. Technicians and optical systems jointly inspect paint finish, panel gaps, and trim alignment. Any detected inconsistency is corrected at specialized rework stations before the vehicle re-enters the line. Meanwhile, smaller sub-assemblies such as the infotainment display, center console, and control switches are inserted into the interior. The navigation unit and digital cockpit are connected via data cables routed behind the dashboard. Functional checks verify touchscreen responsiveness and audio output. Seats are powered to confirm adjustment ranges, and the climate control vents are activated to measure airflow uniformity. Robots perform door opening and closing cycles repeatedly to ensure correct alignment and resistance. Each car's digital key and immobilizer are paired with its onboard computer system using encoded transmissions. Software for all electronic control modules is updated via secure local network, flashing the final operational version. Once the vehicle passes all electrical and mechanical verifications, it proceeds to the polishing and finishing area. Soft rotating pads apply micro-abrasive compounds to remove any minute dust nibs from the clear coat surface. Automated buffing arms move in precise circular patterns, producing a deep, reflective gloss. Exterior badges and emblems are applied using positioning lasers that project outlines onto the panels. The final trim pieces, roof rails, bumper inserts, and protective moldings are attached by pneumatic applicators. Quality control systems photograph each car from multiple angles and compare the images to digital reference models, ensuring dimensional and aesthetic conformity. Interior finishing continues with final checks of upholstery, stitching alignment, and component tightness. The glove box, cup holders, and seatback pockets are opened and closed automatically by small actuators to test smooth operation. Airbags are verified through diagnostic simulation, confirming proper circuit continuity without actual deployment. The onboard lighting system is cycled through all modes to ensure consistent illumination, color, and brightness. Sensors embedded in the windshield and mirrors, such as rain and light detectors, are tested under controlled stimuli from calibrated devices projecting simulated conditions. At this point, the completed Q3 advances to the rolling road noise and vibration test. The car drives on rollers while microphones inside the cabin analyze sound frequencies. The system isolates any rattles, hums, or vibrations, allowing rapid correction. Tire uniformity, wheel bearing balance, and engine mounts are all verified simultaneously. The data is automatically uploaded to the vehicle's production file, forming part of its unique digital build record. After dynamic testing, each car enters a final diagnostics bay. Here, the onboard systems perform a complete self-check. Control modules send reports through the vehicle's central gateway, confirming all components function correctly and that no error codes are stored. This step also activates final system personalizations, such as climate regulation profiles and driver assistant sensitivity defaults. The electrical systems then enter standby mode, preparing for the final steps before packaging and delivery. Protective films are applied over the bodywork, mirrors, and door sills. Seat covers and steering wheel wraps are fitted to preserve cleanliness. A robotic labeling arm applies the vehicle identification stickers inside the door frames and under the hood. Tire pressures are set precisely according to transport requirements. Once the protective coverings are in place, the completed car is driven by automated guidance vehicles to the storage area. Rows of freshly built Q3s line the automated parking yard, aligned with millimeter accuracy under the guidance of laser navigation systems. Overhead gantries lift them onto multi-level conveyors leading to transport carriers, completing the continuous, perfectly timed sequence of mass production. The chassis assembly starts with the front and rear subframes. These are welded steel structures designed to hold suspension components, steering racks, and differentials. They are positioned on jigs, where robotic welders and torque guns assemble them with exacting precision. Coil springs, dampers, control arms, and stabilizer bars are fitted next, followed by the brake discs, calipers, and hubs. The steering assembly is mounted to the front subframe with electronic power assist motors already integrated. Each chassis section is then loaded onto automated guided carriers that move them toward the main assembly line. The painted body shells arrive at the trim and final assembly hall suspended from overhead conveyors. The line begins with the marriage station, where the powertrain and chassis meet the body. The shell is lowered slowly by synchronized lifts, while the powertrain assembly rises from below. Precise alignment pins ensure that the mounting points connect seamlessly. Hydraulic tools fasten the main bolts, joining the subframes to the body. Once joined, the vehicle has its structural and mechanical foundation complete. From this point onward, the car takes on its recognizable form as each subsystem is installed in a coordinated progression down the moving line. At the next stations, fuel and brake lines are routed along the underbody using automated dispensing reels and clip applicators. The exhaust system, composed of stainless steel pipes and catalytic units, is mounted underneath and tightened by robots equipped with socket tools. The drive shaft is connected between transmission and rear differential with pre-balanced joints to prevent vibration. Suspension geometry is verified using laser alignment systems that check camber and toe settings while the vehicle is still on its assembly carrier. Electrical system installation begins as an intricate network of pre-assembled wiring harnesses is positioned throughout the interior and engine bay. Each harness bundle is designed for a specific vehicle configuration delivered by sequence-controlled logistics. Robots guide flexible feeders that insert the harnesses into the correct openings, where operators or smaller cobots secure them with clips and connectors. The dashboard, pre-fitted with infotainment screens, air vents, and instrument clusters, is lifted as a complete module into the cabin and secured to mounting brackets by automated torque tools. Steering columns and pedals are attached next, aligning perfectly with the interior framework. Before packaging and dispatch, every Audi Q3 undergoes a comprehensive final calibration and data synchronization stage that ensures all mechanical and digital systems operate in unison. This stage begins in the electronic validation corridor, a long enclosed section of the production line lined with diagnostic antennas and infrared communication nodes. Each vehicle is powered on and linked wirelessly to the plant's central control network. The system uploads detailed configuration data, engine mapping parameters, suspension profiles, lighting signatures, and connectivity protocols. Firmware versions are checked against master specifications, and any discrepancies trigger an automatic software flash update. This ensures uniform performance across every unit produced in the same series. Once digital synchronization completes, the car moves onto a static test platform that verifies body integrity under controlled vibration. The vehicle is placed on 4 independently oscillating plates that simulate road irregularities. Accelerometers inside the cabin detect structural resonance frequencies. The data is compared with reference profiles to confirm that every weld, adhesive joint, and fastener maintains correct rigidity. Any deviation outside limits prompts a rapid structural audit. This process, though, invisible to the eye, guarantees that all body shells meet precise stiffness and acoustic standards before delivery. After structural validation, the vehicle advances to the dynamic wheel alignment verification system. The car rolls slowly through a track lined with laser emitters that read the wheel angles in real time as the suspension flexes under simulated load. Electronic actuators automatically adjust camber, caster, and toe if necessary, using torque-controlled tools to fine-tune the geometry. A calibration robot checks steering center position by rotating the wheel and comparing sensor readings from the steering column encoder. Once alignment values match the target configuration, the system saves them to the vehicle's digital certificate, ensuring traceability of every adjustment. From there, the Q3 enters the drivetrain verification zone. The car's engine is restarted and coupled via rollers to a chassis dynamometer capable of simulating gradients and acceleration cycles. Sensors embedded in the floor measure traction distribution and torque delivery in real time. The vehicle performs short, controlled accelerations, testing the synchronization of the dual-clutch transmission and verifying that each gear engages at precise torque thresholds. Automated monitoring software evaluates turbocharger boost curves, throttle response, and idle stability. The results are displayed on large control panels above the test cell, color-coded to indicate pass, fail conditions. Once validated, the car proceeds to the acoustic fine-tuning station. In this sound measurement enclosure, microphones capture frequencies from the engine, exhaust, and cabin systems. Robotic arms equipped with parabolic sensors sweep around the vehicle, identifying sources of noise peaks. Engineers use this data to refine sound dampening materials and optimize sealing for future production runs. For each vehicle, if a minor resonance exceeds the standard, automated sealant applicators add micro layers of damping foam at pre-calculated points along the firewall or floor tunnel. The entire process occurs in under 3 minutes, without any interruption to the production flow. Next, the vehicle transitions to the electronic driver assistance calibration area. Here, radar, LiDAR, and camera systems undergo precise adjustment. The car positions itself on a marked platform surrounded by optical reference targets, geometric panels printed with coded patterns. Cameras within the front grille, windshield, and mirrors scan these patterns, while computers calculate alignment offsets. The system adjusts internal parameters electronically, eliminating any optical distortion. Radar units are tested for range and reflection accuracy using robotic targets that move at variable speeds across the room. Each sensor's calibration data is stored in the vehicle's control memory, ensuring full synchronization of the driver assistance suite. Following this digital verification, attention turns to climate and comfort systems. The Q3 enters a sealed environmental chamber where temperature and humidity can be altered rapidly. The cabin is cooled to near freezing, then heated to simulate summer conditions. Sensors monitor air distribution, fan output, and temperature gradients across all vents. Automated detectors ensure even climate performance for every seat zone. The air conditioning compressor cycles through various loads, and the airflow response is recorded. Acoustic sensors measure fan noise levels to maintain comfort standards. After this sequence, the system returns to neutral conditions, and the car exits the chamber fully validated. Exterior illumination testing is performed in the photometric tunnel. This long corridor features black, non-reflective walls and precision photodiode sensors arranged at multiple distances. The Q3's headlights, taillights, and indicators are activated sequentially. Light intensity, beam spread, and color temperature are measured. Adaptive matrix LEDs project controlled patterns on the test wall, which are analyzed for sharpness and uniformity. Rear lamps undergo a similar process, verifying brake and turn signal timing. Once lighting compliance is confirmed, the system stores calibration codes within the lighting control unit. At the next section, all the car's communication systems are evaluated. The onboard infotainment and connectivity modules are powered on and linked to test networks simulating navigation satellites, cellular communication, and Wi-Fi environments. The antennas, hidden within the roof module and mirrors, are tested for signal strength and interference resistance. audio system testing follows immediately afterward. Robotic microphones record tonal balance across all seating positions, while test tones play through each speaker. The equalization algorithm adjusts frequencies automatically, ensuring consistent audio across the vehicle. The final configuration is unique to each car and stored digitally before shipment. After electronic validation, final fluid top-offs are performed. The engine oil, brake fluid, and coolant levels are rechecked by automated sensors. If slight discrepancies exist due to earlier testing cycles, the refilling system dispenses exact volumes to restore optimal levels. Tire pressure sensors automatically communicate with a central control tablet that confirms pressure uniformity across all four wheels. Once all systems are balanced, the car proceeds toward final inspection. The final inspection area is a bright, continuous corridor where every aspect of the vehicle is examined under intense white light. The body passes through a tunnel lined with diffused LED panels that reveal surface irregularities invisible under standard lighting. Automated camera arrays photograph each section of the body, hood, doors, roof, fenders, and compare the images pixel by pixel against a master reference model. Deviations beyond a few micrometers are flagged instantly. If necessary, robotic polishing arms equipped with fine microfiber pads correct localized imperfections in seconds. Inside the vehicle, another series of robotic scanners evaluates interior uniformity. They verify that stitching lines on seats are perfectly parallel, that dashboard gaps remain even, and that switch illumination is consistent. Automated hands actuate every switch, knob, and lever, while optical sensors measure feedback force and travel. Ventilation louvers are opened and closed, cup holders deployed, and glove compartments tested for smoothness. All these motions are logged automatically, creating a full mechanical signature for each vehicle. As inspection concludes, a comprehensive water and air sealing verification is performed once again, this time using ultrasonic testing. The car enters a silent chamber where high-frequency transducers emit sound waves around the exterior. Microphones inside detect whether any sound penetrates through seals. If the readings remain below threshold, sealing is confirmed complete. If not, targeted resealing robots apply micro-adjustments. This non-destructive method ensures long-term insulation without disassembly. The final mechanical action occurs at the wheel torque recheck station. Precision torque arms verify that each wheel bolt maintains the specified clamping force. The tools record each measurement, and any deviation prompts automatic retightening. Brake pedal resistance, steering free play, and clutch pedal calibration are also confirmed through robotic actuation. With mechanical and digital systems finalized, the car advances toward packaging and pre-shipment conditioning. Protective wrapping begins with a conveyor system that positions translucent film over the roof, hood, and rear hatch. Air jets remove dust before automated rollers press the film down evenly. A second machine applies foam blocks beneath the underbody at key contact points for transport stability. Plastic wheel covers and mirror guards are clipped on automatically. Interior protective plastics are sealed around seats and instrument panels to preserve them during transit. Each Q3 is then placed onto an automated transfer dolly, guided by floor-embedded magnetic strips leading to the logistics hall. Here, robotic arms lift the vehicle slightly and slide it onto its designated steel pallet. The palletized cars form precise rows on multi-level conveyors, each position registered by laser sensors for inventory tracking. The entire system functions like a continuous mechanical flow, moving dozens of cars simultaneously toward the storage platforms. Before departure, every car's onboard battery receives a controlled charge cycle to reach standardized voltage levels for storage. Diagnostic systems verify that the electrical load remains stable under low current drain. The vehicle's power management module then enters transport mode, reducing standby power consumption. Each Q3's unique build data, including serial numbers of critical components and calibration records, is uploaded to the master production database. The vehicle is now officially recorded as complete. At the end of the line, automated guided vehicles transport finished Q3 units toward the distribution yard. Overhead cranes lift them onto multi-level carriers that move through an automated scanning gate. This gate performs one final laser measurement of the vehicle's outer dimensions to confirm proper alignment and secure placement on the carrier platform. The cars are arranged in compact formations, their reflective coatings shining under the overhead floodlights. Every movement, from initial body stamping to final loading, is timed, sequenced, and logged within the factory's digital control architecture. To understand the making of a Honda Civic, we must start long before the wheels ever touch asphalt. At the very genesis of the production journey, the press shop. It is here, in a thunderous hall lined with towering metal-forming presses, that raw coils of rolled steel arrive from trusted suppliers. These steel coils, typically delivered on massive trucks or freight trains, are carefully quality checked for thickness, tensile strength, and surface consistency. Technicians inspect the incoming steel with precise ultrasonic and magnetic sensors, looking for any hidden flaws that might affect structural integrity. Once verified, the steel coils are loaded onto an unwinding line and fed into massive blanking presses, machines that slice sheets to exact dimensions for body panel stamping. This stage is not about shape yet. It's about preparing the right size of metal blanks that will later be contoured into the Civic's recognizable exterior components. Each blank is fed robotically into a deep draw stamping press, some of which exert more than 2,000 tons of force in a single downstroke. These presses contain die sets, essentially giant molds machined to micrometer tolerances, which shape the flat blanks into complex three-dimensional parts: doors, hoods, quarter panels, floor pans, and roof skins. The stamping process is both violent and elegant. With each press cycle, a blank disappears between the dies, emerging seconds later with ridges, folds, and curves now embossed into the once flat steel. Robotic arms then transfer these parts to stacking racks with vacuum grippers, organizing them for their next destination, the body shop. If the press shop is the forge, the body shop is the sculpture studio. It's here that the Civic begins to take on its distinctive silhouette. Using a mix of robotic welders, jigs, and human technicians, the various stamped body panels are aligned with incredible precision. Fractions of a millimeter make all the difference in structural rigidity and door fitment. The underbody is constructed first. Floor pan, frame rails, and cross members are robotically welded together in massive fixtures that hold them square. These sub-assemblies are then mated with the upper body structure, including the firewall, roof bow, and side panels. The process of joining these panels together is an art form in itself. Honda uses a combination of spot welding, where copper-tipped electrodes pass current through panels to fuse them, and laser welding, which offers even greater strength and less distortion. Each Civic contains thousands of spot welds, each one measured by inline sensors for penetration, pressure, and temperature. In certain areas, structural adhesives are also applied robotically before parts are pressed together, increasing torsional stiffness and reducing vibration. As the body shell, now called the body in white, progresses through the line, it moves through various stations where more components are added: inner reinforcements, mounting brackets, and crash structure members. Robots ensure these parts are always placed in precisely the same position on every vehicle. The body is then passed through a computerized vision inspection system, which scans it in real time for dimensional conformity. If anything is off, even by a millimeter, it is flagged and corrected immediately. With the body in white completed, the The Civic now advances to one of the most critical and carefully controlled areas in the factory, the paint shop. Before any color can be applied, the raw steel must be prepared with a meticulous cleansing process. The car shell is first subjected to a multi-stage bath sequence in giant dip tanks that use alkaline detergents to remove oils, dust, and microscopic particles left over from stamping and welding. The shell is rotated robotically through each tank, allowing it to be completely submerged and ensuring even coverage across all surfaces, both exterior and hidden interior cavities. After cleaning, the body enters an e-coat bath, short for electrophoretic deposition coating. In this step, the shell is electrically charged and dipped into a tank filled with a water-based primer containing corrosion-inhibiting particles. The electrical charge causes the primer particles to be attracted and evenly bonded to the body's surface. This layer not only improves paint adhesion, but provides crucial rust protection, especially in inner cavities that are hard to reach with spray guns. Once the e-coat is cured in an oven at around 180 degrees Celsius, the Civic moves into the primer application booth, where robotic arms spray a base primer coat across the shell. This step evens out the surface texture and prepares it for color paint. Following a short curing phase, the vehicle is moved into the color booth, a climate-controlled, dust-free chamber where the final paint coat is applied. Each Civic model has its own unique paint codes, which are carefully loaded into robotic arms that spray layer upon layer of base coat and clear coat in a highly choreographed dance. The painting process is arguably one of the most mesmerizing stages to witness. 12-axis robotic arms glide effortlessly around the car body, their movements pre-programmed down to the millisecond, ensuring consistent paint thickness and flawless coverage. The color coat is followed immediately by a layer of clear coat, which adds depth and gloss while protecting the finish from UV light and environmental damage. After curing in a second oven for up to 40 minutes, the freshly painted Civic body emerges gleaming, but still empty. Just a hollow shell with no glass, no engine, no wheels. That's about to change. The next phase, is the trim and chassis marriage line, where the Civic's raw body begins to transform into a fully outfitted vehicle. This is where thousands of individual parts, from wiring harnesses to dashboard assemblies to seatbelt retractors, are installed piece by piece, each in a strictly orchestrated order that has been optimized for both ergonomic efficiency and production speed. Before any of that happens, however, the body must be precisely prepared for the installation of glass. Robots apply urethane adhesive beads around the front and rear window openings, and then suction-equipped robotic arms carefully position and press fit the windshields and back glass into place. Smaller fixed windows are installed similarly. These adhesives not only secure the glass, but also provide structural rigidity and watertight sealing. Inside the cabin, the assembly line team begins installing sound deadening mats, interior wiring looms, dashboard subframes, HVAC ducting, and insulation panels. Every cable must be routed correctly through predefined paths using color-coded guides and clips to avoid interference or rattling. Robots and technicians work side by side. Robots handling repetitive or awkward tasks such as bolting down seat frames or placing door wiring clips, while humans complete more dexterous jobs like feeding dashboard harnesses through tight spaces. In a parallel part of the factory, just as precise and choreographed as the main body line, the powertrain assembly line is busy bringing together the mechanical heart of the Honda Civic. Here, in a series of carefully timed workstations, the engine block, cast from aluminum alloy at an off-site foundry, is delivered for the beginning of what will become a highly intricate construction process. The raw engine block, a silvery rectangular core with machined bores and passages, is first mounted to an adjustable rotating stand that allows technicians and robots to access all angles of the component with ease. Technicians begin by installing the crankshaft, main bearings, and connecting rods, each component measured to precise tolerances using torque wrenches and digital sensors. The pistons are inserted and aligned with the cylinders, lubricated and checked for correct seating before the cylinder head is mounted and bolted down in a strict torque sequence. Fuel injectors, spark plugs, oil pans, gaskets, and camshafts are all installed in sequence. Robotic arms place timing chains or belts, set cam phasing, and verify timing alignment using vision inspection systems that reference QR codes and part markings. Once complete, each engine goes through a cold test station where sensors check oil circulation, compression ratios, and component tolerances without actually firing the engine. If the unit passes, it continues down the line to be joined with the transmission, either a continuously variable transmission, 6-speed manual, or in some markets, a traditional automatic. These transmissions arrive from specialized Honda transmission plants and are pre-assembled with clutches, gears, and hydraulic valve bodies already in place. The marriage of engine and transmission is done with the help of alignment jigs and torque-monitored bolt drivers to ensure perfect balance and alignment. This combined powertrain module is then sent via automated guided vehicle to the chassis line, where other sub-assemblies, such as the front subframe, suspension arms, steering rack, and exhaust system, are already being built up. In this stage, the Civic's front and rear subframes are assembled separately, each housing the relevant suspension geometry, control arms, sway bars, and dampers. These are pre-torqued and inspected before being mated to the powertrain and chassis cradle. Once this fully assembled underbody unit is complete, it moves via overhead conveyor to the marriage station, a dramatic intersection of the trim line and the chassis line. The painted body shell, with dashboard and interior partially installed, is suspended above the cradle. Slowly, the two converge. Using laser guidance and a complex hydraulic lift system, the car body is lowered onto the powertrain module with millimeter precision. Specialized guide pins ensure perfect alignment, and robots immediately begin bolting the chassis and body together at multiple mounting points. This process, known as the body drop or marriage, represents one of the most pivotal points in the Civic's construction. In just a few minutes, the car transitions from a hollow shell to a complete vehicle with drivetrain, suspension, and steering components now integrated. From here, the assembly line continues with intense precision as the Civic begins to come alive, inch by inch. The next station involves connecting electrical harnesses and fluid lines. Large modular connectors are snapped into place, linking the vehicle's main computer systems, ECU, sensors, transmission control, and lighting. Brake lines, fuel hoses, coolant pipes, and air conditioning refrigerant lines are connected with quick coupling fittings that are color-coded and pressure-tested for leaks. Robots insert and fasten fuel tanks underneath the chassis, followed by heat shields and underbody panels that protect the car's systems from road debris and temperature extremes. Meanwhile, technicians inside the vehicle are installing the instrument panel, infotainment system, airbag modules, and steering wheel. The center console and infotainment head unit are test-fired on the spot, using a temporary power source to ensure all touchscreens, audio systems, and onboard diagnostics are functional. Seats arrive pre-assembled from a separate supplier and are robotically positioned, bolted down with monitored torque drivers, and electrically connected for airbag and heater functions. Simultaneously, the doors, which were removed earlier in the process to improve access during interior assembly, are now reattached by a series of 6-axis robots. These machines lift the doors from their carriers, align them to body datum points, and bolt them onto reinforced hinges with a precision that's been pre-calibrated using 3D body scans taken earlier. Technicians then install seals, trim pieces, weather stripping, and window regulators before the power windows are connected and tested electronically. Next comes the installation of exterior lighting. Headlamps and taillights are snapped into place with molded brackets, fastened with screws and bolts, and connected via waterproof electrical connectors. Each light module is briefly illuminated to confirm functionality and correct alignment. The front grille, bumper fascias, and underbonnet components, such as the air intake ducting, battery, and fuse boxes, are added next. Every step in this stage is monitored in real time by a central production server that tracks torque readings, scan codes, and pass/fail diagnostics from every tool on the line. With nearly all physical components in place, the Civic is almost complete, but not quite ready to leave the line. Next, the wheels and tires are installed. Tires arrive from Honda's tire supplier, already mounted and balanced on alloy wheels. They are indexed and attached to the hub assemblies using robotic wheel guns calibrated to apply the exact torque specification for each lug nut. These specs vary depending on wheel size, market, and drivetrain layout. An automated alignment station immediately follows, where high-speed cameras and laser sensors measure and adjust toe, camber, and caster angles on all four wheels. These adjustments are performed automatically by robotic arms that adjust the suspension linkages without human input. The engine is now ready for its first breath of life. The car is filled with all necessary operational fluids: engine oil, transmission fluid, coolant, windshield washer fluid, brake fluid, and refrigerant. These fluids are dispensed using automated boom systems that identify the vehicle model via RFID tags and fill to precise volumes using flow sensors. Then, the Civic moves into the initial startup bay, where for the first time, its ignition is triggered. An onboard computer runs a rapid series of checks on fuel pressure, ignition timing, emission systems, and electrical networks. If any error code is flagged, the vehicle is diverted for diagnostics. If everything checks out, the Civic proceeds. Following startup, the vehicle undergoes a dynamic rolling test on a set of inline dynamometers. The car's wheels are driven at varying speeds while technicians monitor acceleration, braking, gear shifting, and engine response. Noise, vibration, and harshness levels are recorded using microphones and vibration sensors in key areas. The vehicle's radar, sonar, and camera-based safety systems, like lane keeping assist and adaptive cruise control, are also calibrated using test targets and moving objects. Even the horn and windshield wipers are tested as part of this comprehensive validation. Once mechanical systems are signed off, the Civic advances to the water test booth, an enclosed tunnel fitted with high-pressure nozzles simulating rain and storm conditions. The car is sprayed for several minutes from all angles to ensure no water leaks into the cabin or trunk. Any intrusion, however slight, results in the vehicle being pulled for resealing and retesting. After the water test, the Civic passes through the final inspection bay. Here, a team of trained inspectors examine every surface of the car under bright, full-spectrum lighting to detect paint imperfections, panel misalignments, or blemishes. Doors, hoods, and trunks are opened and closed repeatedly to confirm proper fit and latch operation. Interior materials are checked for stitching quality, switch function, and material alignment. Even the scent of the cabin is evaluated to ensure consistency with Honda's brand standards. Once it clears final inspection, the Civic is driven briefly to a short holding area where any software updates are flashed into the ECU, infotainment system, and onboard diagnostics. The vehicle's VN is laser etched into the frame and stored electronically in Honda's global database. The car is now officially considered production complete. With the vehicle officially signed off from the production line, the next phase of the Honda Civic's journey is handled by a specialized logistics team responsible for organizing and staging vehicles for transport. At this point, every Civic has its final configuration, its color, trim level, engine variant, transmission type, and region-specific features all set in stone. But before it's shipped off to a dealership or distribution hub, it enters what's known as the Vehicle Outbound Logistics System. In a vast open-air vehicle yard adjacent to the assembly facility, often spanning hundreds of acres, you'll find hundreds, even thousands, of freshly minted Honda Civics parked in rows that stretch toward the horizon. This yard is not simply a parking lot, it's a tightly managed inventory control zone that functions like a living spreadsheet. Each Civic is tagged with an RFID chip or barcode label that links to a digital manifest. These digital profiles contain everything about the vehicle: where and when it was built, its VIN, trim level, market destination, port of discharge if being exported, and even its assigned dealership. Before entering this staging area, each vehicle is given a final scan at the gate. This scan confirms the completion of software installation, quality checks, and fluid top-offs. Once scanned, a logistics automation system assigns a parking spot based on the vehicle's outbound path. Cars, headed for rail transport, are parked near the loading tracks. Those bound for container shipping are staged by the dock ramps. Regionally distributed vehicles are positioned near road freight terminals. Each parking operation is choreographed with the help of a fleet of vehicle movers, some human, some automated. In newer facilities, autonomous electric tugs shuttle completed cars to their assigned staging rows, minimizing fuel usage and reducing human error. As the Civic arrives at its designated position, it is double-checked for cosmetic integrity. No scratches, no dents, and no contaminants like bird droppings or sap that could damage paint before delivery. Depending on the region, the vehicle may receive a light protective wrap, plastic sheeting on the hood, roof, and doors, as well as foam bumpers or wheel covers. These additions protect the finish during transport, particularly when Civics are being shipped across long distances via rail or ocean freight. From here, distribution diverges based on geography. Civics bound for nearby regions are typically loaded onto multi-level auto transport trucks, known as car haulers, using a hydraulic ramp system that maximizes vertical space. Each trailer can accommodate 8 to 10 vehicles, depending on size and configuration. Loading these haulers is a skillful job. Drivers must navigate tight clearances, especially when reversing a Civic up a narrow ramp just inches from another car's bumper. Once secured, the transport trucks depart along pre-planned routes, tracked in real time with GPS and monitored for weather, traffic, and delivery schedules. Vehicles typically arrive at regional distribution centers or directly at dealerships within 24 to 72 hours of departure, depending on distance. But for Civics headed overseas, the process is even more elaborate. Vehicles scheduled for export are transported to a port of exit, usually via rail. Special rail cars, called autoracks, are designed for this purpose. They're 3 levels high and feature secure wheel chocks, enclosed sides to protect from the elements, and locking mechanisms to prevent vehicle movement during transit. Before boarding the train, each Civic goes through a brief pre-rail inspection, checking tire pressure, door latches, and fuel levels. Vehicles must carry just enough fuel for loading and unloading, nothing more. Once the autoracks reach a port, often within a few days, the Civics are offloaded and prepped for ocean shipping. At the port, Honda works with marine logistics providers to board the vehicles onto roll-ons or roll-off vessels. These are essentially floating parking decks that can carry thousands of cars at once. A team of stevedores and vehicle handlers drives each car onto the ship via massive loading ramps. The cars are parked tightly together, locked down with wheel straps, and catalogued by location and destination. Each ship carries a mix of vehicles headed to different global markets, with each deck subdivided by destination. During the sea journey, which can last anywhere from 2 to 6 weeks, depending on the destination, the vehicles remain dormant but protected. Temperature, humidity, and salt exposure are controlled to prevent corrosion. Some ships use dehumidification systems to further protect sensitive electronics and cabin components. Upon arrival at the destination port, be it Vancouver, Rotterdam, Sydney, or Tokyo, the Civics are offloaded and moved to an inbound vehicle processing center. Here, local Honda representatives carry out market-specific inspections and final preparations. Depending on regulations and consumer preferences, some components may be installed at this stage. Market-specific infotainment systems, badges, labels, or compliance stickers. The battery is checked, tire pressure adjusted for the regional climate, and the vehicle is detailed one final time. Then, and only then, does the Civic make its final trip to a dealership, where it will be test-driven by prospective buyers and eventually become part of someone's daily life. The journey from raw steel coil to showroom floor is now complete. But behind this process is something even more impressive than the car itself: the manufacturing ecosystem that made it all possible. Every Honda plant, whether in Canada, Japan, the United States, or Thailand, is a model of lean manufacturing. Honda is one of the pioneers of flexible assembly, meaning the same line that produces the Civic may also produce other models with minimal downtime between them. This flexibility allows the plant to respond to shifting market demands without reconfiguring the entire factory. The chassis platform used by the Civic, for instance, might also underpin the Honda HR-V or Insight, all of which can be built on the same line with different modules and components swapped in real time. This orchestration relies on an advanced system of just-in-time supply chain logistics. Rather than stockpiling parts on-site, Honda's suppliers deliver components like dashboards, seats, HVAC modules, and wiring harnesses exactly when they're needed, often arriving at the plant just hours before installation. This minimizes inventory costs and allows for rapid changes to production volume or specification. Each component comes pre-labeled with a digital build sheet that identifies exactly which Civic it's meant for, ensuring flawless sequencing on the line. Complementing this is the just-in-sequence system, which goes one step further, delivering parts in the precise order of vehicle production. For example, if the assembly line is building a red Civic Sport, followed by a blue Civic X, the bumpers, headlights, and infotainment units for each car arrive in that exact order, pre-arranged for immediate installation. It's a ballet of logistics that requires real-time communication between Honda's central production servers and hundreds of Tier 1 and Tier 2 suppliers. To keep everything running smoothly, predictive maintenance is used throughout the plant. Equipment sensors track vibration, temperature, load, and wear in everything from conveyor belts to robotic welders. When a part shows signs of fatigue, the system schedules preventative maintenance before failure can occur, reducing downtime and improving safety. Quality control doesn't end once a vehicle leaves the line. Each factory maintains a dedicated audit station where randomly selected Civics are pulled for intensive testing. These vehicles are dissected and reviewed by expert inspectors who examine weld quality, paint thickness, body fitment, software behavior, and road performance. This data is fed back into the production process to flag trends or emerging issues, enabling Honda to respond proactively and maintain consistent quality. In terms of environmental responsibility, Honda's Civic production lines are engineered for energy efficiency and waste reduction. Water used in the paint booth is recycled through filtration and reverse osmosis systems. Paint overspray is captured by electrostatic filters and reused. Waste metal from the stamping plant is sorted robotically and returned to the steel mill for remanufacturing. Even the heat from curing ovens is repurposed to warm other parts of the facility. power consumption across the plant is closely monitored and managed. Many Honda facilities are partially powered by solar arrays, wind energy, or cogeneration systems. Advanced lighting systems using motion sensors and LED technology ensure that energy is only used when and where it's needed. In some plants, Honda has achieved near-zero landfill status, meaning almost all waste materials, plastic, metal, rubber, even food waste, are recycled or repurposed in some way. Inside the modern Honda manufacturing plant, what might seem like a chaotic tangle of machines, parts, conveyors, and workers is in fact a precisely engineered environment orchestrated with clockwork efficiency. At this stage of production, where physical assembly transitions into post-production optimization and system refinement, the focus increasingly shifts from brute force manufacturing to intelligent systems management, what Honda refers to internally as manufacturing excellence. At the heart of this excellence is automation, an ever-present, evolving backbone of the modern Civic factory. Over 60% of tasks on the assembly line are now completed or assisted by robots. These are not simple, one-purpose mechanical arms, but intelligent, adaptable systems equipped with high-resolution sensors, 3D cameras, and real-time process feedback. In the body shop, robotic welders do far more than spot weld. They monitor the pressure of each weld in milliseconds, analyze the depth of each fusion, and dynamically adjust parameters to compensate for slight variations in steel thickness or surface contaminants. These adjustments happen in real time, with hundreds of data points captured per second and logged directly into Honda's centralized manufacturing database. Each of these robots is not just a tool, but a node in a larger intelligent network. That network, Honda's digital production control system, is built to track every Civic as it moves through the plant. From the moment a steel blank enters the stamping press to the final torque applied to the last wheel nut, the vehicle's identity is logged and linked to a database of component specifications, supplier batch numbers, sensor readings, machine parameters, and quality checks. This system allows Honda to maintain traceability, a key principle in modern automotive manufacturing. If a defect is ever found in a Civic's transmission casing or infotainment unit, engineers can instantly trace that part back to the day, time, and exact supplier lot it came from. This level of insight allows for surgical product recalls rather than sweeping generalizations, and is a cornerstone of Honda's commitment to quality and customer safety. In many zones of the factory, cobots or collaborative robots are replacing traditional industrial arms. These are smaller, more agile machines designed to work side by side with human operators. Unlike traditional robots that are fenced off behind safety barriers, cobots use proximity sensors, pressure feedback, and vision systems to detect the presence of humans and respond accordingly. For instance, in the trim assembly zone, cobots might assist a technician by precisely positioning heavy dashboard modules while the human secures them in place with fasteners. This reduces operator fatigue and improves assembly consistency, particularly for ergonomically challenging tasks that are difficult to automate entirely. Even AGVs, or automated guided vehicles, have seen substantial evolution. No longer confined to fixed track systems, newer Honda plants use vision-guided or LiDAR-based AGVs that navigate the factory floor independently, rerouting in real time to avoid traffic congestion or bottlenecks. These intelligent carts move everything from seats and dashboards to windshield glass and wiring harnesses, all without human input. Each AGV is linked wirelessly to the central factory control hub, which orchestrates their movements in relation to production flow. They are programmed to deliver specific components to a station at a precise time, synchronized with the exact Civic model being assembled at that moment. And this synchronization is not theoretical. Honda employs a modular assembly system, meaning that various trim levels, Powertrain variants and color options are built on the same line, back to back, without downtime. A Civic Sport with manual transmission might be followed directly by a Civic Touring with a CVT and an entirely different dashboard layout. Each workstation is equipped with smart tools, torque wrenches that automatically adjust to the specification required for that trim, vision systems that verify part fitment, and pick-to-light component bins that illuminate only the exact part required for that vehicle configuration. The system dynamically adapts the line to each unique build without requiring tool changes or reprogramming. In areas such as windshield installation or seat alignment, machine vision systems play a critical role. High-definition cameras capture detailed images of each step in the process, comparing live data to reference models stored in the system. These cameras can detect misalignments as small as 0.2 millimeters and instantly alert workers or trigger robotic correction. If a deviation is beyond correction thresholds, the system flags the vehicle and diverts it to a diagnostic bay for human evaluation. These inline quality checks are far more than visual. They're statistical safeguards, using large data samples to spot trends before they become problems. The paint shop, often one of the most energy-intensive parts of the plant, has also embraced advanced automation. Honda's robots not only apply base coats and clear coats with micron-level consistency, they also self-monitor the viscosity of paint, adjust spray patterns for optimal atomization, and even self-clean their nozzles between cycles. Overspray, which historically represented significant waste, is now captured by electrostatic plates and returned to a closed-loop reclaim system. Humidity and airflow in the paint booths are adjusted in real time to compensate for changes in ambient conditions, ensuring flawless finish consistency across seasons and global regions. Underpinning all of this automation is a layer of predictive analytics. Honda doesn't just react to faults, it forecasts them. Every sensor, robot, conveyor, and torque gun in the plant feeds data into a centralized AI-driven platform that looks for anomalies. If a certain fastener is being torqued more tightly than normal over a series of builds, the system flags the deviation. It may indicate tool wear, part misfit, or an upstream supplier issue. Engineers are alerted before a failure occurs. This predictive maintenance approach has dramatically reduced downtime and improved first-pass yield, an industry metric referring to the percentage of vehicles that pass inspection without needing rework. In the engine assembly hall, torque sensors are so precise they can detect if a technician has even one thread of a bolt cross-threaded. If detected, the system locks the build station, highlights the error on a display, and prevents the engine from moving forward until the issue is addressed. These safeguards ensure that even as production volume increases, Honda maintains the reliability and consistency that the Civic name is built upon. Lighting across the factory is controlled by intelligent energy management systems. LED lights adjust brightness based on time of day, production activity, and occupancy, cutting power usage dramatically. Heating and cooling systems adapt to the number of people in a zone and the thermal load of nearby machines. Even compressed air systems used in pneumatic tools and robotic actuators are monitored for leaks. Any pressure drop triggers an alert and isolates the zone for maintenance. These efficiencies not only reduce environmental impact, but also contribute to cost savings that allow Honda to reinvest in manufacturing innovation. As Civic production continues around the clock, every process, every station, and every worker is part of a living, learning system. The factory itself becomes smarter with time. Lessons learned from one batch of Civics are automatically integrated into subsequent runs. And when a mid-cycle refresh or new feature is introduced, say a redesigned infotainment interface or new powertrain calibration, the change is implemented digitally across the plant. Robots are updated wirelessly with new motion paths. Technicians receive augmented reality instructions via tablet. Parts suppliers are given revised sequencing instructions within minutes. As the Honda Civic continues its evolution on the global stage, one aspect of its production has grown increasingly central to the company's mission: sustainability. Manufacturing a modern automobile like the Civic requires immense amounts of energy, materials, water, and logistics, all of which must now be managed under the pressure of carbon emissions reduction and environmental stewardship. Honda's response to this challenge has been far from superficial. In many ways, its Civic production lines have become test beds for the company's broader efforts in building low-impact, resource-efficient factories. Every modern Civic plant is built with environmental performance targets baked into its architecture. From the outset, Honda employs what it calls Green Factory Principles, a framework of metrics and strategies for reducing energy consumption, carbon footprint, chemical emissions, and waste. These principles are applied at every level, from site selection to machinery operation. One of the most visible aspects of this sustainability initiative is Honda's aggressive use of renewable energy sources. Several Civic production plants, such as the one in Greensburg, Indiana, use large-scale solar panel arrays to offset electricity usage. These panels are often installed on the roofs of buildings or in dedicated solar fields adjacent to the facility. While they may not yet power the entire operation, they significantly reduce reliance on fossil fuels and provide a stable energy source for specific systems like lighting grids or HVAC. In addition, some facilities make use of combined heat and power systems, also known as cogeneration units, which burn natural gas to generate electricity on-site while capturing waste heat to provide hot water and climate control. These systems can be more than twice as efficient as pulling electricity from the grid alone, significantly cutting greenhouse gas emissions per kilowatt hour used. But it isn't just energy that's optimized. Water usage is a critical sustainability issue, particularly in the paint shop, where thousands of liters are required daily for rinsing, cleaning, and chemical mixing. Honda's solution has been the implementation of closed-loop water recycling systems. These systems use a mix of ultrafiltration membranes, reverse osmosis, and UV sterilization to clean and recirculate water through the plant. In some factories, as much as 95% of water used in production is reclaimed and reused. The E-Coat dip tanks, for example, are now topped off with recycled water that meets near laboratory-grade purity standards. Chemical usage in painting and metal treatment processes has also been re-engineered. Honda has transitioned many of its surface preparation and cleaning solutions to low VOC and phosphate-free alternatives. This not only reduces hazardous waste, but also improves worker safety and air quality inside the factory. Ventilation systems are fitted with electrostatic scrubbers and HEPA filters to capture overspray particles and solvent vapors, reducing emissions that would otherwise enter the atmosphere. Solid waste is handled with equal intensity. Modern Honda Civic plants operate on a near zero landfill policy. That means virtually all manufacturing waste, scrap metal, plastics, rejected parts, packaging materials, even cafeteria waste, is sorted, recycled, or repurposed. Steel offcuts from the stamping shop, for instance, are collected automatically by magnetic conveyors and baled for return to the steel mill. Plastic injection molding runners are ground up on site and reintegrated into new parts. Waste lubricants are filtered and reused for non-critical applications. To track the progress of these initiatives, every plant maintains a real-time environmental dashboard, visible to both operators and management. This dashboard displays metrics like kilowatt hours per car produced, liters of water used per cycle, paint shop VOC emissions, and recycling rates. Engineers use this data to identify inefficiencies and launch Kaizen initiatives, small, continuous improvements that ripple across departments and compound over time. These dashboards are also shared across Honda's global factory network to spread best practices from one facility to another. That global network is itself a masterclass in distributed manufacturing. Unlike some automakers that rely on a single central plant for specific models, Honda's Civic production is distributed across multiple countries. This includes facilities in Japan, the United States, Canada, the United Kingdom, Thailand, and others depending on generation and market. Each of these plants is capable of localized production, a practice where the Civic is manufactured with regional suppliers, regulations, and consumer preferences in mind. For instance, Civics built for the North American market may feature different safety systems, infotainment options, or climate control calibrations than those produced for Southeast Asia or Europe. This localization reduces the carbon footprint of global shipping, lowers costs, and allows Honda to respond quickly to local demand. Supporting this decentralized system is a globally synchronized digital architecture. Through Honda's Global Production Operations System, every plant can access standardized blueprints, torque specs, quality benchmarks, and real-time engineering updates. If a supplier in Thailand discovers a defect trend in a batch of brake calipers, that information is immediately shared across the entire network, triggering preemptive inspections in other factories and supplier audits if necessary. It's a powerful example of how data is now just as important as steel in car manufacturing. These global factories are also adapting to accommodate a rising wave of powertrain diversification. As demand for cleaner transportation grows, Honda has committed to electrification, not just in full EVs, but also in hybrid and plug-in hybrid variants. For the Civic line, this means that certain factories now have dual powertrain capability, allowing them to produce both internal combustion and hybrid electric Civics on the same line. This feat of integration requires major adjustments to logistics, assembly sequencing, and training. Hybrid Civics require the installation of battery packs, inverters, high voltage wiring, and regenerative braking systems, all components absent in a traditional Civic. These parts arrive from Honda's dedicated eDrive suppliers, or in-house battery module assembly units. Once in the plant, they are carefully synchronized with the hybrid vehicle builds using the same just-in-sequence delivery system used for conventional components. Specialized battery handling equipment is required to safely transport and install the high-voltage packs, which are typically mounted beneath the rear seat or trunk floor. Technicians working in these zones receive additional safety training and wear insulated gloves, tools, and personal protective equipment. The factory floor is also reconfigured to include voltage-safe testing bays, where hybrid Civics undergo electrical system calibration, battery charge verification, and inverter diagnostics before leaving the plant. Furthermore, Honda is increasingly experimenting with modular EV production cells, small, independently operable lines dedicated to electric vehicle production. While not yet widespread for Civic manufacturing, these modular cells are being piloted as scalable units that can be added to existing facilities as EV demand grows. Their flexible footprint and self-contained operation allow them to be spun up quickly in response to market shifts. There's also a growing presence of simulation-driven design in the manufacturing pipeline. Before a new Civic variant ever hits the factory floor, it is built virtually inside a high-resolution, physics-accurate 3D model of the plant. Engineers can simulate every weld, fitment, fastener torque, and wiring route before any physical part is produced. These simulations help identify potential interference issues, ergonomic challenges, or inefficiencies long before they reach real workers or robots. The result is faster model ramp-up, fewer line stoppages, and improved first-time quality. Even the training of plant staff is evolving. New workers learn procedures not just from manuals or trainers, but through augmented reality overlays that guide them step by step. Wearing AR glasses or using tablets, they can see animated instructions projected onto real parts, highlighting the correct bolt, identifying the right clip location, or warning about torque sequence. This immersive training dramatically shortens the learning curve and reduces mistakes. Through all of these innovations, sustainable processes, global synchronization, powertrain diversification, and smart manufacturing technologies, the Honda Civic continues to set the standard for what a mass-market, high-efficiency automobile production line can achieve. And it does so not with gimmicks or short-term fixes, but with systems thinking, scientific rigor, and decades of accumulated expertise. The production of a Tesla vehicle begins long before any car takes shape on the assembly line. Deep within the vast expanse of a Tesla Gigafactory, a meticulously orchestrated sequence of processes brings together raw materials, robotics, and human ingenuity to transform aluminum, lithium, silicon, and countless other elements into one of the most advanced electric vehicles on the planet. From the first bolt of sheet metal to the final pixel on the touchscreen interface, every component is born of a vision rooted in automation, precision, and sustainability. We begin with the raw materials that will ultimately form the structural skeleton of the car. Aluminum coils. These massive, industrial-grade aluminum rolls are delivered to the stamping facility in pre-cut widths and are carefully inspected for thickness consistency, surface finish, and chemical composition. Tesla predominantly uses high-strength aluminum alloys for many of its structural components due to their lightweight yet durable properties. These alloys are crucial to achieving Tesla's performance goals without sacrificing efficiency or safety. As each coil is unspooled, it is fed into a massive blanking press, a machine capable of cutting large sheets into specific dimensions called blanks. These blanks, often the size of a car door or hood, are prepped for the stamping process, where one of the most visually dramatic parts of the car's creation takes place. The stamping area, often housed in its own building due to the sheer vibration and noise, is where enormous dies, precision-engineered molds weighing several tons, shape these blanks into panels that will form the body-in-white structure of the car. Each die is lowered into a stamping press, often a servo-driven press with forces exceeding 5,000 tons. These machines exert immense pressure in milliseconds, forming the aluminum blank into complex geometries. Multiple stages of stamping may be needed for a single panel, including draw, trim, pierce, and flange operations. After stamping, robotic arms lift and transfer the formed panels onto conveyor belts, directing them to a quality inspection zone where laser scanners and human inspectors check for warping, stress marks, or micro cracks. Any deviation from tolerance can compromise fit or function and is promptly rejected or reworked. While the body panels are being shaped, another process begins deep inside the battery cell manufacturing area. Tesla, being vertically integrated, produces many of its own lithium-ion battery cells. Raw materials such as nickel, cobalt, manganese, and lithium carbonate are transported into specialized mixing tanks where they undergo slurry formation. These slurries are spread onto copper and aluminum foils, which are then dried in a vacuum oven to form electrodes. Once the electrodes are prepared, they are calendared, flattened to precise thicknesses, and wound or stacked into cylindrical, pouch, or prismatic cells depending on the vehicle model. Each cell is filled with electrolyte solution and hermetically sealed in a dry room to prevent moisture contamination, which could compromise safety or performance. These cells are then loaded into battery modules using robotic pick-and-place arms, which align and connect the terminals with extreme accuracy. The modules are assembled into packs, which include integrated cooling channels, structural support, and electronic control units. These battery packs will eventually be installed into the vehicle's underbody, providing both power and structural rigidity. Back in the body shop, the stamped aluminum panels are robotically welded and riveted together to form the body in white, the term for the car's skeletal shell before any paint or interior components are added. Tesla employs a combination of laser welding, spot welding, and structural adhesive bonding to fuse panels together with minimal distortion and maximum strength. Hundreds of robotic arms suspended from overhead gantries work in synchronized motion, welding, clamping, positioning, all choreographed with software that can adjust in real time based on tolerances and feedback. Laser scanners constantly monitor joint integrity and positional accuracy, ensuring that each weld is correctly formed and precisely located. The body in white at this stage is a gleaming raw aluminum shell, unpainted but fully formed, with all major exterior panels in place, including doors, hoods, and trunk lids, which are often removed and processed separately for better access and quality control. The next destination for the body is the paint shop, one of the most complex and environmentally controlled areas of the entire factory. Before painting can begin, the aluminum body must undergo a chemical pre-treatment process that removes oils, residues, and impurities. This is achieved by submerging the body in a series of baths, alkaline cleaners, deionized water rinses, and ultimately a zirconium or phosphate-based conversion coating that promotes adhesion and corrosion resistance. After drying in an oven to eliminate residual moisture, the body moves into the electrocoating tank, or e-coat stage. Here, the entire shell is submerged in a bath of electrically charged paint particles, which uniformly coat every crevice and interior cavity, ensuring anti-corrosion protection even in areas never visible to the customer. The body is then baked in a curing oven to harden the coating and prepare it for the next layers of paint. The painting process involves multiple coats: primer, base coat, and clear coat. Each coat is applied in sealed spray booths using high-precision atomizing robots, which follow programmed trajectories to ensure even coverage. Advanced electrostatic spray techniques are used to minimize overspray and improve efficiency. After each coat, the vehicle passes through a series of flash and bake ovens to dry and cure the paint, creating the high-gloss finish Tesla vehicles are known for. Once painting is complete, the body heads to the general assembly area, where it begins to transform from an empty shell into a fully operational vehicle. But before any parts are installed, the body undergoes another round of rigorous inspections. Laser alignment systems, gap and flush measuring tools, and robotic probes verify dimensional consistency across every surface. Any discrepancies are flagged and corrected before proceeding. Simultaneously, thousands of components are arriving from various sub-assembly lines and suppliers, including the interior trim, seats, dashboards, glass, wiring harnesses, and powertrain modules. These parts are delivered using automated guided vehicles, AGVs, that navigate the factory floor using embedded magnetic strips or LiDAR-based systems, ensuring just-in-time delivery with minimal human handling. The interior assembly begins with the installation of wiring harnesses, which are laid throughout the vehicle like a nervous system. These harnesses, containing kilometers of wire, are clipped into designated paths along the floor, pillars, and roof. Robots and human technicians work together, ensuring connectors are correctly routed and terminals are securely fastened. Next, the HVAC components, dashboard structure, and infotainment systems are installed, followed by airbags, sound insulation, and seat frames. At each step, torque-controlled tools and digital confirmation systems ensure that every fastener meets the required specification. The vehicle's panoramic glass roof, a signature element of Tesla's design language, is then lowered into place using vacuum suction lifters and laser-guided alignment tools. A two-part adhesive is applied by robotic nozzles to create a watertight seal. The doors, previously processed separately, are reattached and calibrated to ensure perfect alignment and smooth operation. Tesla's frameless door design and automatic opening features require particularly tight tolerances and sensor calibration. With the interior taking shape, the vehicle proceeds to powertrain integration, where the battery pack, assembled and tested in a parallel process, is lifted by robotic jigs and bolted into the vehicle's underbody using a sequence of torque-controlled actuators. The drive units, whether dual or tri-motor, are then installed onto the front and rear subframes, connected via suspension arms and motor mounts that are pre-aligned using precision fixtures. With the battery pack securely mounted and the drive units in position, the vehicle is now ready to undergo one of the most critical transitions in the entire manufacturing process: electrical and software activation. While the car may appear nearly complete, it is still lifeless. No lights, no screen activity, no sensor communication. This stage, often referred to as initialization, is where the vehicle essentially takes its first breath. A technician connects a diagnostic interface to the vehicle's central computer, usually via a secure data port under the dash, and uploads the foundational firmware that activates the vehicle's electronic control units, or ECUs. Each Tesla contains dozens of ECUs distributed throughout the chassis, responsible for everything from motor control to autopilot systems, battery thermal regulation, infotainment, and safety monitoring. Tesla's approach to software architecture is notably centralized compared to traditional automakers. Instead of relying on fragmented systems developed by various suppliers, Tesla has developed an in-house software stack that enables over-the-air updates, real-time diagnostics, and direct integration between mechanical systems and the vehicle's neural net. Once the firmware is loaded, a cascade of subsystems begins to power on. The touchscreen illuminates for the first time. The instrument cluster boots up. Cameras begin streaming to internal diagnostics. Every sensor, switch, and relay goes through a self-check process that verifies communication with the vehicle's central gateway. Any issues, such as a disconnected wire, a miscalibrated radar unit, or a sensor failure, are immediately logged for remediation. At this stage, even something as minor as a single LED malfunction will halt the progression until it's resolved. Next, attention turns to calibrating the advanced driver assistance systems. Tesla's autopilot suite relies heavily on an array of forward, rear, and side-facing cameras, ultrasonic sensors, and radar or LiDAR, depending on the model and hardware iteration. These units must be precisely aligned within the bodywork to ensure accurate environmental perception. Calibration is not just mechanical, but also algorithmic. As the vehicle is rolled into a controlled calibration zone, a series of reference panels, patterns, and 3D markers are placed around the car. Cameras are activated, and software compares live imaging data against known coordinates to fine-tune the visual input. The system will not pass if even a single camera is slightly skewed or obstructed. Following this, the wheels and tires are mounted, another process where automation and precision intersect. Each wheel assembly, comprising the tire, alloy rim, TPMS sensor, and balancing weights, is prepared in an adjacent sub-assembly cell. Robotic arms select the correct wheel variant depending on trim level and mount it onto the vehicle's wheel hub using torque-monitored tools. Once installed, the wheels are not yet fully ready for the road. They must be aligned. Wheel alignment takes place on a dedicated platform, where laser or camera-based alignment tools measure caster, camber, and toe angles in real time. Adjustments are made on the spot using robotic wrenches that turn suspension bolts until readings fall within micrometer level tolerances. Proper alignment is vital, not only for performance and safety, but also for autopilot accuracy. as steering bias or drift could interfere with the vehicle's self-driving capabilities. Now we arrive at one of the most impressive parts of Tesla's assembly process: final assembly verification and end-of-line testing. This begins with a full-body water intrusion test. The completed vehicle is driven, or in some cases, automatically transported, into a sealed chamber known as the water test booth. High-pressure nozzles blast the car from all directions, simulating rain, puddle splashes, and pressure washing. Sensors inside the cabin monitor for even the slightest moisture intrusion. Any leak, even a trace around the door seals or underbody joints, results in a stop and targeted repair. Once the vehicle passes the water test, it moves into dynamic testing. But before that can begin, it must first pass a rolling road diagnostic check. The vehicle is positioned on a set of rollers that simulate driving conditions. Here, Tesla technicians run through a wide range of operational checks. Motor response is tested across a variety of simulated terrain profiles. Regenerative braking systems are evaluated to confirm energy recovery rates match expected values. HVAC systems are activated to check for proper airflow, temperature regulation, and acoustic performance. Inside the cabin, the touchscreen interface undergoes a systems integrity test. Each menu, function, and button is activated in sequence. The infotainment system is tested for connectivity to Tesla's software servers. Navigation modules are initialized. Bluetooth and Wi-Fi antennas are pinged. Microphones and speakers are checked for distortion or static. The cabin camera, located near the rearview mirror, is tested for focus and response to light changes. The glove box, front latch, trunk motors, and window regulators are also checked for proper operation and speed. After static diagnostics, the vehicle is finally ready for its low-speed dynamic test. On-site test tracks, usually located adjacent to or within the Gigafactory premises, allow each vehicle to undergo a short but comprehensive road test. The driver is usually a trained Tesla technician who runs the car through a prescribed routine: acceleration from 0 to moderate speeds, emergency braking, tight cornering, and high-speed lane changes. This test evaluates suspension response, noise levels, steering feel, and drivetrain behavior under real load conditions. The vehicle's software continues to log performance data throughout the drive, flagging any anomalies. After returning from the test track, the car enters the final visual inspection area. Here, a team of human inspectors armed with light panels, bore scopes, and digital checklists reviews every visible surface inside and out. Paint quality is scrutinized for orange peel texture, swirl marks, or dust nibs. Panel gaps are measured by hand and with laser gauges. The interior is inspected for material alignment, stitching accuracy, and uniform texture. Every single button, vent, trim piece, and fixture is physically touched and verified. If the vehicle passes this multi-layered gauntlet of inspections, it moves into what's known as pack out, the final preparation area before shipment. Here, the car receives its VIN label, ownership documentation, and destination configuration. This is where region-specific software settings, navigation maps, and language preferences are loaded. The final battery charge is administered, usually to around 90%, before the vehicle is powered down and prepared for transport. Each Tesla is now ready to leave the factory, but even this step is a study in logistical precision. Automated systems coordinate the movement of completed vehicles from the final inspection bay to outbound logistics. Depending on destination, the vehicle may be loaded onto a covered rail car, placed into a secure car carrier, or transferred to a nearby delivery hub. RFID tags embedded in the vehicle identify it to tracking systems that monitor its journey to the customer. It is important to note that Tesla's manufacturing ethos is grounded in continuous improvement. Unlike traditional automakers that rely on annual model cycles, Tesla frequently changes its assembly lines in real time. updating hardware or processes based on production learnings, user feedback, and software improvements. This philosophy means that even within the same week, two identical models may have subtle differences in componentry, firmware version, or assembly methods. These continuous upgrades are made possible by Tesla's heavy reliance on vertical integration and factory-level data analytics. Every torque wrench, sensor, robot, and diagnostic station feeds data into a centralized factory control system. Engineers analyze this data daily, making adjustments to improve efficiency, reduce rework rates, and enhance vehicle quality. This feedback loop between digital twin modeling, live production, and field performance is one of the reasons Tesla has been able to scale quickly while maintaining product innovation. With the vehicle now fully assembled, inspected, and approved, it embarks on the final leg of its journey: delivery to the customer. Whether arriving at a showroom, a regional distribution center, or directly to a driveway via Tesla's direct delivery program, the finished product represents not just a vehicle, but the culmination of thousands of interconnected systems working in harmony, each with millisecond-level precision, each tuned for performance, safety, and the future of mobility. Once a Tesla vehicle has cleared its final inspection and receives its shipment authorization, the journey from the Gigafactory to the customer begins. Unlike conventional auto manufacturers, which often rely on third-party dealership networks and extensive warehousing chains, Tesla's direct-to-consumer delivery model has radically simplified and streamlined this phase. Yet, behind that apparent simplicity lies a highly coordinated logistical infrastructure, optimized to handle the massive volume of vehicles produced daily across multiple global factories. At this stage, the vehicle is routed into a specialized outbound logistics yard, a designated section of the Gigafactory site, or an adjoining facility engineered specifically for the staging, sequencing, and transportation of finished vehicles. Each car is tagged with a digital shipping label that contains its vehicle identification number, model variant, color, wheel configuration, destination, and special instructions such as left-hand versus right-hand drive. This digital manifest is cross-referenced with Tesla's centralized logistics control software, ensuring that each car is placed into the correct regional batch for dispatch. Automated tug vehicles, similar to those used in airport ground operations, tow trailers of Tesla vehicles into position. If the vehicle is destined for domestic delivery, it is typically loaded onto a car carrier truck designed to hold 7 to 10 units. These carriers are scheduled to depart in tightly timed intervals, with software routing each truck for the most efficient delivery path based on real-time traffic, weather, and destination inventory levels. For international shipments, the process shifts slightly. Vehicles bound for overseas markets are loaded onto rail cars or container haulers that transport them to port facilities. At the port, the vehicles are driven onto roll-on/roll-off ships, a type of cargo vessel with built-in ramps and internal decks specifically designed for transporting cars. Each Tesla is parked and secured inside the vessel, often alongside other vehicles of the same batch, in a configuration that minimizes offloading time upon arrival. Throughout this journey, every vehicle remains digitally visible to Tesla's logistics team. GPS tags, onboard cellular connectivity, and carrier integration systems allow real-time tracking from the moment the vehicle leaves the plant to the moment it is delivered to the end customer. This level of transparency enables Tesla to forecast delivery windows with a high degree of accuracy and proactively resolve issues like weather delays or customs bottlenecks. Meanwhile, Tesla's delivery centers and service hubs are preparing to receive the vehicles. These locations, often converted warehouse spaces or minimalist showrooms, act as regional fulfillment points. Upon arrival, each vehicle undergoes a final pre-delivery inspection. This includes checking tire pressures, topping off windshield washer fluid, confirming that the software version is current and ensuring the paint and interior remain in pristine condition. The protective coverings applied during shipment, such as plastic seat covers and foam door guards, are removed, and the car is detailed for presentation. If a customer has opted for Tesla's home delivery option, the vehicle may be dispatched from the delivery center directly to the buyer's driveway using either a flatbed or a mobile technician. Tesla's minimalist approach to delivery day often involves minimal paperwork, since much of the ownership transfer process is handled digitally ahead of time. Customers sign final documents electronically, receive a tutorial on using their new vehicle via the in-car interface or mobile app, and are given access to Tesla's expansive digital support ecosystem. But delivery is not the end of the story. It's merely the handoff point between manufacturing and long-term ownership. Tesla's commitment to post-production support is tightly integrated into its digital platform. The same software and hardware systems that facilitated the car's birth on the factory floor now serve as tools for its ongoing evolution. Over-the-air updates are one of the most defining characteristics of the Tesla ownership experience, and they depend on a robust ecosystem of remote diagnostics, data collection, and machine learning feedback loops. Every Tesla on the road constantly reports anonymized performance data back to Tesla's servers. This includes battery health, motor efficiency, navigation anomalies, autopilot behavior, sensor readings, and even software bugs. Engineers at Tesla's headquarters use this data to refine algorithms, push updates to correct inefficiencies, and enhance safety features, all without the owner needing to visit a service center. This dynamic software lifecycle, enabled by the tightly coupled manufacturing and software teams, makes Tesla vehicles unique in their ability to improve long after leaving the factory. Meanwhile, Tesla's service infrastructure continues to grow alongside its production volume. Instead of relying entirely on traditional service centers, Tesla employs a mobile service strategy wherever possible. These service vans are equipped with diagnostic tools, replacement parts, and certified technicians who can perform a wide range of repairs or updates at the customer's location. The ability to diagnose and even preemptively fix issues before they affect the driver is rooted in the precision and data fidelity achieved during the original manufacturing process. Looking back toward the factory, it's important to understand how Tesla's architectural philosophy supports this entire life cycle. Every gigafactory is designed not just to build vehicles, but to serve as a data hub, a testing ground, and a self-improving machine. These plants are built with flexibility in mind, using modular assembly lines that can be reconfigured on the fly. Instead of fixed conveyor belts, Tesla often uses autonomous mobile robots and smart material flow systems that can reroute components or vehicles as production needs change. The Gigafactory floor is not one continuous line, but a series of interconnected stations. Each one is equipped with sensors, machine vision, and feedback modules that report into a central factory operating system. This system not only tracks current production metrics, but also simulates process optimizations. For example, if a torque reading at a robotic arm consistently falls within the low-end threshold, engineers can be alerted and update the robot's behavior before a quality deviation even occurs. This predictive control approach reduces downtime and increases first-pass yield, meaning more vehicles pass inspection on the first try without needing rework. Vertical integration plays a critical role in making this system work. Tesla doesn't just assemble parts, it manufactures many of them. From battery cells to electric motors, from infotainment chips to firmware code, Tesla has brought traditionally outsourced operations in-house. This reduces dependency on suppliers, shortens feedback loops, and allows the company to innovate rapidly. For instance, if a new battery chemistry is developed in Tesla's R&D lab, pilot-scale production can begin almost immediately within a section of the existing gigafactory, without the need for third-party approval or infrastructure overhaul. Even Tesla's supply chain reflects this philosophy of speed, control, and adaptability. Critical materials like lithium, nickel, and cobalt are sourced through long-term contracts with mining operations. And in some cases, Tesla has invested directly in extraction or refinement operations. These materials are routed directly to gigafactories or regional production hubs, bypassing many of the bottlenecks that affect traditional automakers who rely on complex supplier tiers and international freight forwarding. This system is further enhanced by Tesla's real-time digital twin architecture, a virtual replica of the entire manufacturing process. Every machine, part, and process is mirrored in a digital environment that can simulate disruptions, forecast efficiency gains, and run hypothetical scenarios. Want to test how a new weld technique might affect throughput? The digital twin can simulate that change in minutes, allowing engineers to make data-backed decisions that translate directly into physical adjustments. Through all of these layers, physical infrastructure, software integration, vertical manufacturing, and delivery logistics, Tesla has redefined what modern automotive production looks like. It's not just about building cars, it's about building a system that builds itself smarter with every iteration. Every vehicle produced feeds data back into this system. Every manufacturing anomaly becomes a learning opportunity. Every software update enhances not just the product, but the factory's ability to produce the next one even better. What this means is that the gigafactory isn't a static building. It's a living organism, a self-correcting, self-improving entity designed not only to produce cars, but to redefine what a car even is in the age of autonomy, electrification, and artificial intelligence. And at the center of this vision lies a carefully choreographed dance of machinery, people, data, and innovation, all working in harmony to create not just a vehicle, but a new standard for the global auto industry. Inside a Tesla gigafactory, perhaps the most mesmerizing and defining visual is the near-symphonic choreography of robots working in harmony. Tesla employs tens of thousands of industrial robots across its global facilities, many sourced from automation giants like KUKA and FANUC, and many others developed in-house. But these aren't the slow, single-arm welders of traditional auto plants. These are high-speed, multi-axis machines operating in tightly coordinated clusters that resemble mechanical dance troupes, fast, precise, and relentlessly efficient. The bulk of these robots are deployed in the body shop, where raw stamped panels are joined to form the body in white. Here, multiple robot arms work within inches of one another, one positioning a panel, another applying structural adhesive, and a third completing a weld, without ever colliding. This level of spatial awareness is made possible by a digital supervisory system that orchestrates each motion path in microseconds. Each robot is fitted with a suite of sensors, including force feedback, proximity detectors, and sometimes even cameras, allowing them to adapt slightly if a panel is marginally misaligned or a weld point needs micro-adjustment. In many production cells, Tesla has implemented what are known as friction stir welding units, robots capable of joining aluminum panels without melting them. This technique, originally developed for aerospace manufacturing, uses a high-speed rotating tool that generates frictional heat to soften and fuse materials without introducing impurities or thermal distortion. It results in stronger joints and is especially effective for joining thick battery pack casings or high-stress structural nodes. But Tesla's automation does not end at the mechanical level. Surrounding the physical robots is a vast digital control infrastructure powered by machine learning algorithms that analyze every torque value, weld voltage, and robot movement. These systems compare every single action against historical data to identify patterns that may indicate future faults. For example, If a particular welding arm shows a slight uptick in motion latency or current draw, the system can schedule predictive maintenance before a full failure occurs. This predictive maintenance loop dramatically increases uptime and reduces unexpected halts in the production line. Complementing this robotic workforce is a carefully integrated human team. Contrary to the misconception that gigafactories are purely robotic, Tesla maintains a robust human workforce in areas where judgment, dexterity, or problem solving are still superior to automation. For instance, interior trim installation, particularly tasks involving soft materials like Alcantara, stitched leather, or delicate wiring, still relies on trained technicians who can feel for correct tension, align materials by eye, and make subtle corrections during fitment. Human workers are also essential during final inspection, dynamic testing, and exception handling. If a part doesn't meet specifications, or if a software glitch prevents a subsystem from booting, it's often a human specialist who diagnoses and resolves the issue. These employees are equipped with digital tablets linked to Tesla's internal manufacturing cloud. They receive live data feeds from the vehicle's onboard sensors and can pull up schematics, tolerances, and previous production history in seconds. Every fix they apply, every note they enter, becomes part of that car's digital footprint, a log that follows it forever, even into post-sale diagnostics. Tesla's approach to worker efficiency is also shaped by ergonomic engineering and cognitive load optimization. Workstations are designed to reduce repetitive strain injuries with tool arms that balance heavy equipment and lift assists for placing components. Augmented reality overlays are sometimes used during training phases, projecting digital guides onto surfaces to help new employees understand complex assemblies. Rotational schedules ensure workers shift between physically demanding tasks and more routine duties, helping prevent fatigue-related errors. As we dig deeper into the brain of the Gigafactory, we arrive at what is perhaps Tesla's greatest long-term differentiator: the use of artificial intelligence, not just in the vehicles, but within the factory itself. Tesla doesn't merely automate individual machines, it trains its factories to optimize themselves. This is achieved through a combination of real-time data ingestion, cloud-based analytics, and reinforcement learning loops. Let's take an example from the paint shop. Traditionally, robots follow predefined spray paths based on CAD data. However, Tesla trains its painting robots using vision-based systems that analyze each body shell in real time for curvature, panel orientation, and gap uniformity. This data informs dynamic adjustments to spray trajectory, nozzle pressure, and stroke timing. The result is more uniform coating, fewer touch-ups, and improved long-term finish durability. Or consider battery pack assembly. Each cell inserted into a module is monitored for voltage, internal resistance, and capacitance. Tesla uses this data to build a profile of every module's thermal characteristics. If a pattern of abnormal cell degradation is observed in the field, engineers can trace it back to the exact production batch, process variables, or even environmental conditions at the time of assembly. This data loop enables retroactive improvements to manufacturing conditions and helps refine pack longevity models for future software updates. One of the more futuristic systems Tesla is rolling out across its newer gigafactories involves swarm intelligence for material transport. Rather than fixed conveyor systems, Tesla uses fleets of autonomous mobile robots that navigate the factory floor using SLAM algorithms. These robots aren't programmed with fixed paths. They learn optimal routes in real time, adapt to obstacles, and communicate with one another to avoid collisions or bottlenecks. This approach allows the factory layout to be more modular and reconfigurable, supporting agile production and faster adaptation to new models or variants. Equally fascinating is Tesla's use of simulation environments for factory operations. Entire sections of the Gigafactory are mirrored in a digital twin. an exact 3D replica of the physical space and its processes. Engineers can run simulations to test new workflows, evaluate machinery upgrades, or even plan how to integrate a new vehicle platform without ever disrupting the live production line. If a simulated robot collision is detected, the system can suggest path modifications or sequence changes before real-world implementation. This same philosophy extends to Tesla's use of custom silicon chips. While best known for its full self-driving computer, Tesla also designs specialized hardware for internal factory use. These include image recognition chips optimized for high-speed defect detection, edge computing units for data processing at the machine level, and embedded control systems that allow more precise energy regulation in welding and curing ovens. This level of hardware customization provides Tesla with granular control over quality, energy efficiency, and process speed. Another compelling layer of Tesla's factory evolution involves environmental engineering. Every gigafactory is designed with sustainability as a core tenet. Rooftop solar arrays, on-site water recycling systems, and battery-powered internal logistics vehicles are just some of the components contributing to closed-loop manufacturing. The energy used to produce each Tesla vehicle is increasingly being sourced from renewable systems within the facility itself, dramatically lowering life-cycle carbon emissions. Tesla's focus on vertical integration again becomes critical here. When energy systems, battery chemistry, robotics, and software all originate from the same corporate ecosystem, coordination becomes exponentially easier. Design tweaks to the battery casing, for example, can immediately inform changes to the casting molds, welding fixtures, or software-based thermal models, without the friction of cross-company coordination. Perhaps the most emblematic symbol of this holistic integration is Tesla's gigacasting machines. These are among the most powerful aluminum die casting machines in the world, capable of creating entire underbody sections as a single solid piece. These machines, designed in partnership with Audi, reduce the number of parts in the vehicle's chassis from hundreds to just a few, eliminating fasteners, reducing weight, and improving crash performance. Integrating such massive components into the production line requires not just physical reconfiguration, but software integration, supply chain alignment, and real-time QC adaptation, all of which Tesla is uniquely positioned to manage in-house. As we look at the sum of all these systems, robotics, AI, digital twins, human-machine interfaces, gigacasting, and energy-conscious infrastructure, it becomes clear that the Tesla production process is not simply a variation on traditional automotive manufacturing. It is an entirely new operating system for building cars. A platform, not just a plant. A fusion of machine intelligence, predictive analytics, physical innovation, and agile design thinking, all operating under a single cohesive philosophy. The Tesla Gigafactory isn't just where vehicles are built. It's where ideas are born, tested, scaled, and refined in real time. Where the boundary between hardware and software dissolves. Where every sensor, every weld, and every decision feeds back into a growing repository of knowledge that powers the next generation of vehicles, robots, factories, and systems. One of the most disruptive engineering breakthroughs in Tesla's modern manufacturing playbook is the integration of the structural battery pack, a complete rethinking of how the battery, chassis, and underbody of the vehicle work together. In traditional automotive design, the battery pack is a standalone component, an energy container bolted to the car's underbody. But in Tesla's structural pack architecture, pioneered with the 4680 battery format, the battery no longer rides beneath the structure, it becomes the structure. To understand the scale of this shift, we first need to explore the 4680 cell itself. Named for its dimensions, 46mm wide and 80mm tall, The 4,680 cylindrical lithium-ion cell represents a significant departure from the older 2170 and 18650 formats. It offers 5 times the energy, 6 times the power, and reduces the cost per kilowatt hour significantly. But it's not just the size that matters, it's how the cells are built and what they enable downstream in manufacturing. Each 4,680 cell is designed to support tabless internal architecture. In conventional cells, current must travel through a tab, a narrow conductor that can create resistance and heat. In Tesla's tabless design, the entire edge of the rolled electrode acts as a current collector, enabling more uniform heat distribution and higher current throughput. This drastically reduces internal resistance, improves efficiency during charge and discharge, and simplifies thermal management, a critical benefit when assembling high-density battery modules. These cells are produced in a vertically integrated line that starts with electrode slurry mixing, followed by coating, calendaring, cutting, and winding, all performed under strict environmental control. The wound jelly rolls are inserted into steel canisters, filled with electrolyte, sealed by laser welding, and then aged, tested, and sorted. What's remarkable is that Tesla's battery lines are not just production machines, they are learning machines. Each stage of battery cell production is heavily instrumented, with sensors that track viscosity, coating uniformity, line tension, and thermal behavior. These metrics feed back into AI-driven quality control systems that adapt in real time, reducing scrap rates and improving yield without requiring line shutdowns. Once the cells are complete, they are no longer assembled into modules as in traditional EVs. Instead, Tesla places them directly into the structural battery pack housing, eliminating intermediary module structures. This pack is a part of the vehicle's load-bearing frame, not an add-on. The cells are bonded in place using structural epoxy, and this bonded matrix provides rigidity akin to an aircraft's wing box design, a technique borrowed from aerospace engineering. A critical enabler of this approach is the use of high-performance structural foams and thermal adhesives. These materials serve multiple functions simultaneously. They manage vibration and noise, conduct heat away from the cells to integrated cooling loops, and crucially, form part of the vehicle's crash energy management system. During side or front impacts, the structural battery pack helps distribute forces across a wider area, reducing localized deformation and improving occupant safety. In the Gigafactory, structural pack assembly is a distinct line physically separate from standard battery operations due to its unique tooling requirements. Cells are loaded into the pack casing using high-speed robotic insertion machines. Adhesive dispensing systems apply precisely metered quantities of 2-part epoxy at high pressure. Once cells are in place, the entire structure is cured in massive industrial ovens that bring the adhesive to full mechanical strength. After cooling, the pack undergoes precision machining to create interfaces for the drive unit, seat mounts, and body attachment points. What results is not just a battery, it's a central element of the vehicle's physical frame. The top of the pack often serves as the interior floor of the cabin. The bottom, reinforced by ribbed aluminum or composite materials, acts as the underbody and aerodynamic tray. By combining energy storage, structural support, and crash safety into a single unit, Tesla eliminates dozens of separate components, reducing mass, simplifying manufacturing, and slashing costs. Now, integrate this with another innovation, gigacasting. Tesla's use of giant aluminum die casting machines to form the front and rear underbody sections of its vehicles is nothing short of revolutionary. These Idura Giga Press machines, weighing over 400 tons and applying clamping forces in the range of 6,000 to 9,000 tons, can create entire frame sections as a single cast. Instead of welding together hundreds of stamped components, Tesla now forms massive structural elements in one shot, lighter, stiffer, and far faster to produce. When the front and rear castings are combined with the central structural battery pack, Tesla essentially builds the entire underbody of a vehicle using just 3 large parts. These unibody trios replace what was once over 300 parts in older chassis architectures. This not only reduces complexity and assembly time, but also minimizes the number of suppliers, welds, fixtures, and potential quality defects. Each casting is inspected via X-ray and ultrasonic imaging to detect porosity, cracks, or incomplete fills. Any anomalies are rejected and remelted, maintaining a closed-loop aluminum recycling system. This radical simplification also redefines how the rest of the car is built. Traditional automotive factories are organized around a highly linear body-in-white process, frame construction, then floor pan, then underbody integration. Tesla's method is more like assembling a modular aircraft, where large sub-assemblies are brought together at fewer, more tightly controlled junctions. This allows Tesla to create more compact factories with faster cycle times and fewer workers per unit produced, metrics that directly impact capital efficiency and return on investment. To support these next-generation designs, Tesla continues to invest heavily in materials science research, much of it focused on high-strength aluminum alloys, advanced polymers, and die-casting feedstock refinement. The development of proprietary aluminum alloys that combine excellent flow characteristics in casting with high tensile strength post-treatment is a crucial part of making gigacasting work. These alloys must cool evenly, avoid brittleness, and withstand both crash loads and environmental exposure over time. In parallel, Tesla is exploring dry electrode manufacturing for future battery lines, a technique that eliminates the solvent-heavy coating and drying stages currently used in electrode production. Dry electrodes can be applied directly to the current collector using pressure and heat, significantly reducing energy consumption, production footprint, and cost. This aligns with Tesla's vision for more sustainable, vertically integrated gigafactories, ones that consume fewer resources per gigawatt hour and can be rapidly scaled in new geographies. Indeed, Tesla's goal is not just to build more cars, it's to scale manufacturing like a technology company, not an industrial one. This means shorter ramp-up times, smaller capital expenditures per unit of output, and a globally unified software-hardware stack that can be deployed anywhere in the world with minimal localization. Future gigafactories, like those planned in Mexico and India, are being designed with these structural pack and casting concepts at their core, meaning they won't just produce the next generation of Tesla vehicles, they will be born already optimized for speed, simplicity, and flexibility. This systems thinking extends even further into factory floor layout and material flow logistics. With fewer total parts, Tesla can implement straighter, more continuous material pathways, reducing the need for kitting, buffering, and material staging. Instead of having dozens of sub-assembly lines feeding hundreds of components, Tesla can deliver entire modules, like castings or packs, straight to the marriage station, where the vehicle begins to take its final form. This layout change reduces floor space, lowers error rates, and improves throughput. It also allows for greater software simulation of factory dynamics. When each vehicle only passes through 30 or 40 production cells, rather than 200 or 300, it becomes computationally feasible to simulate the entire factory in real time. AI-based systems can then test flow changes, balance labor loads, and reroute production if a bottleneck emerges, all before any change is implemented on the floor. The result is a self-learning, self-optimizing factory capable of adapting to demand shifts, supplier disruptions, or design updates faster than legacy automakers can retool a single line. All of this innovation, structural batteries, 4,680 cells, gigacasting, and software-first factories converges into a clear strategic objective: build more cars, better and faster, with fewer people and lower capital costs per unit. It's not about squeezing the last drop of efficiency from legacy systems. It's about replacing those systems entirely. And the boldness of that approach is why Tesla's manufacturing story remains one of the most closely watched industrial transformations of the 21st century. To understand how a Toyota car is made, one must first step into a space where discipline, precision, and respect for process define every movement: the Toyota factory. Within these facilities, the transformation from raw materials to a fully functional vehicle is not simply a mechanical progression, but a living manifestation of a philosophy. This philosophy, known globally as the Toyota Production System, or TPS, is centered on two foundational pillars: Jidoka, automation with a human touch, and just-in-time manufacturing. Together, these principles dictate how every Toyota vehicle is born. Imagine walking into one of Toyota's flagship plants, such as the Tsutsumi plant in Toyota City, Japan, or the Georgetown facility in Kentucky. The air is filled not with chaos, but with a quiet, rhythmic hum. It is not the sound of urgency, but of synchronization. Workers, robots, and machines operate in precise harmony, each step of the process unfolding like clockwork. Every bolt tightened, every part aligned, every inspection performed. Nothing is rushed, but nothing is delayed. The objective is not to build fast, but to build flawlessly, and in the smallest increment of time and resource necessary. The beginning of any Toyota vehicle starts far upstream, not in the plant itself, but in the raw material supply chain. Toyota sources high-strength steel, aluminum, plastics, semiconductors, glass, and countless other materials through a tightly managed supplier network. Each supplier is held to stringent quality and delivery standards. Deliveries arrive at the plant just in time, often within hours of their use. This lean inventory philosophy reduces waste and ensures that the factory remains agile, able to adapt to shifting demands or changes in vehicle variants without maintaining massive backstocks. Once materials arrive, the first physical steps in vehicle creation occur in the stamping shop. Here, massive coils of steel or aluminum are loaded into enormous stamping presses, machines that weigh hundreds of tons and exert enough force to shape thick metal in a single, clean motion. These presses are fitted with die sets, precision-engineered molds that stamp out individual body components like fenders, hoods, roofs, and doors. The dies are swapped out by automated systems within minutes, allowing the line to shift seamlessly between models with minimal downtime, a critical capability in a mixed model facility. The stamped panels are then transported, often via overhead conveyor systems or autonomous carts, to the welding shop, the domain of the body in white. Here, the core structure of the car takes shape. Robotic arms, fitted with weld guns and sensors, orchestrate a ballet of sparks. These machines are programmed with exacting specifications to apply spot welds at predefined intervals, securing body panels together into a rigid, cohesive structure. Human technicians oversee the process, performing inspections, handling complex geometries, and activating andon systems, alert cords, should any defect be found. Toyota's concept of Jidoka is exemplified here. Each welding station is empowered to halt the entire line if a defect or misalignment is discovered. This is not seen as failure, but as a safeguard for quality. Rather than allow a potentially flawed product to progress, the issue is stopped at its source, analyzed, and resolved before production resumes. Workers are trained not just to follow instructions, but to improve the process. This continuous improvement culture, known as Kaizen, is deeply embedded in every team member, from entry-level assemblers to plant managers. Once the car body has been assembled and verified for dimensional accuracy using laser measuring systems, It proceeds to the paint shop, where it is cleaned, sealed, primed, and finally painted. Before any color is applied, the body is immersed in a series of baths for electrodeposition coating, a process that prevents corrosion by electrically bonding a primer to the metal surface. The body then moves through a drying oven before entering the color application booths. Inside the paint booths, robotic arms fitted with rotary atomizers apply successive layers of primer, base coat, and clear coat. Each coat is inspected under intense lighting and humidity-controlled conditions to ensure consistency and to prevent inclusions such as dust or overspray. Technicians perform visual inspections and touch tests, sometimes sanding and reapplying paint if surface imperfections are found. The body then enters a final curing oven, where it is baked at high temperatures to harden the paint finish. By now, the car's basic structure is complete and coated, but it still lacks its soul: the engine, drivetrain, electronics, and interior. These elements come together in the general assembly area, a zone that stretches across hundreds of meters and involves hundreds of interwoven processes. It is here that Toyota's just-in-time philosophy truly comes alive. Unlike traditional batch manufacturing, Toyota's production line is mixed model, meaning different car types and trims, even with different engines or drive systems, are produced on the same line in whatever sequence is dictated by real-time customer orders. To accommodate this, parts are delivered in sequence to the line. If the next car is a Corolla hybrid with a panoramic roof, the exact seat configuration, roof headliner, battery pack, and other components for that configuration arrive seconds before the car reaches the station where they'll be installed. One of the most critical events in the assembly process is known as the marriage, the point at which the painted body is lowered onto the pre-assembled chassis. The chassis includes the engine, transmission, suspension components, exhaust system, and drivetrain. These assemblies are built up in parallel lines and synchronized with the main body line so that both components arrive at the marriage station at precisely the same moment. As the body descends onto the chassis, guided by precision jigs and hydraulic lifts, technicians align mounting points and fasten critical bolts using torque-controlled tools. Every fastening operation is digitally logged and monitored. If a bolt is under or over-torqued, or if a tool slips, the system immediately alerts the operator. These digital confirmations ensure traceability and enable Toyota to maintain records for every car that leaves the factory, supporting future warranty claims, recalls, or quality assurance audits. After marriage, the car begins to take on its recognizable interior form. Dashboards are installed as single pre-assembled units, often produced by Tier 1 suppliers in nearby satellite facilities and delivered just in sequence. Seats, wiring harnesses, air conditioning modules, infotainment systems, and airbags are carefully installed in a series of tightly choreographed steps. Workers use a combination of hand tools, smart torque guns, and pick-to-light systems, which light up the exact part bins for each operation to ensure accuracy and speed. This process continues with the installation of glazing, lighting elements, bumpers, wheels, and various trim components. Every part is fitted under strict quality standards with gap alignment and surface flushness, checked visually and digitally using laser systems. During each step, workers remain empowered to pull the and-on cord if they detect an anomaly, reinforcing Toyota's belief that quality is built in, not inspected in. Once the assembly is complete, the vehicle is no longer a shell or a skeleton. It is a living machine, but one that has not yet been proven. The next phase will test every system, calibrate every sensor, and ensure that the Toyota badge on the front carries with it the weight of reliability, safety, and trust. Following the completion of physical assembly, each Toyota vehicle enters one of the most critical phases of the production lifecycle: the inspection, calibration, and functional testing stage. This is where mechanical craftsmanship meets analytical scrutiny. Every car must now prove that it not only fits together correctly, but that every system operates as designed, with the precision and reliability Toyota is globally known for. The first area the vehicle enters is typically the initial quality gate. Here, a multi-point check is performed by trained inspectors who methodically examine structural components, body alignment, and basic mechanical fitment. Every door, trunk, and hood is opened and closed to assess alignment and sound. Uneven gaps, misaligned panels, or abnormal resistance are noted and corrected on the spot. Workers use gap gauges, flushness sensors, and manual inspection tools to detect even the smallest deviations in build quality. From there, the vehicle proceeds to dynamic system checks. This is where the car begins to come to life, electronically and mechanically. A technician connects the vehicle to a factory diagnostic system, uploading the final software package to all electronic control units. In a modern Toyota, there can be 30 to 80 ECUs depending on the model, each managing a different subsystem, such as braking, power steering, stability control, hybrid drive, airbag systems, and infotainment. The ECUs are flashed with firmware specific to the car's trim level, engine type, and market destination. This step is highly sensitive, with redundant data verification systems to ensure the software uploads completely and correctly. Once configured, the system initiates a global self-check, where the vehicle essentially performs a diagnostic scan of itself. Each ECU confirms its functionality and readiness, while the technician monitors for error codes or inconsistent behavior. Any anomaly is logged and triggers a deviation procedure where the vehicle may be diverted to a separate diagnostics bay for deeper troubleshooting. Next, the car is transferred to a specialized station for fluid filling and pressure testing. Here, automated systems dispense exact volumes of engine oil, brake fluid, coolant, washer fluid, and, for hybrid or electric models, inverter coolant or battery thermal management fluids. These filling stations are digitally calibrated to prevent overfilling or contamination. During this stage, systems are also pressurized and sealed, then tested for leaks using pressure sensors and flow meters. Brake lines are tested by pressurizing the system and monitoring for pressure drops, ensuring every car leaves with a perfect, air-free hydraulic system. At this point, the vehicle is ready for its first engine start. A technician initiates ignition using either a key fob or the factory diagnostic console. The vehicle turns over and the engine comes to life. During this brief but critical startup phase, the system monitors RPM, oil pressure, exhaust sensor feedback, charging voltage, and other vitals. The technician listens for abnormal engine noise, checks idle quality, and watches for leaks or warning indicators. Once the engine stabilizes, the vehicle begins a series of automated or semi-automated functional tests, including shifting through gears, verifying steering assist, and checking basic throttle response. With the engine running and fluid circulating, the vehicle now moves to the dynamic test track or rolling road, depending on the facility's layout. On a rolling road, a stationary test bench with rotating drums. The car is accelerated through a simulated driving sequence. Braking, acceleration, shifting, emissions control, and hybrid transitions are all tested under load. This is where software calibration is fine-tuned. For example, hybrid systems may be evaluated for smooth transitions between electric and gasoline power, while adaptive cruise control sensors are calibrated to recognize distance targets. Meanwhile, headlight aim is adjusted using laser-guided alignment equipment. Wheel speed sensors are tested, and the vehicle's onboard safety systems, such as ABS and traction control, are confirmed to respond appropriately to artificial inputs. On some high-spec models, even the sound insulation is checked using internal microphones while simulating wind and road noise inside a soundproof chamber. Following dynamic testing, the car is driven to a water test booth, an enclosed chamber equipped with high-pressure nozzles, positioned to simulate heavy rain, splash conditions, and high-speed water exposure. The entire vehicle is blasted with water from above, below, and the sides. Technicians inside the booth or using moisture detection tools afterward check the interior for any signs of leakage, particularly around doors, glass seals, sunroofs, and underbody grommets. Vehicles that fail this test are sent to a specialized sealing team for inspection and repair before re-entering the final inspection queue. The penultimate step in the process is the final visual and tactile inspection line, often referred to as the white light tunnel. In this area, powerful overhead lights and side lighting replicate broad daylight, revealing surface imperfections invisible under factory lighting. Inspectors move around each vehicle slowly, checking for micro scratches, paint defects, misaligned trim, dirt under the clear coat, and material inconsistencies. The tactile elements are just as important: seat firmness, stitching alignment, trim tightness, and even the smoothness of control knob rotation are checked against factory benchmarks. Finally, once all systems are verified, paint and finish are pristine, and data records confirm the vehicle's complete build and performance history, the car is released from production. A digital certificate is issued, containing every measurement, torque value, fluid fill, software version, and test result from each phase of assembly. This data is stored in Toyota's secure manufacturing archive and is linked to the vehicle's VIN for life. If a component recall, software update, or warranty claim ever arises, this record becomes the reference point for diagnostic and corrective action. As a last step, protective films are applied to vulnerable surfaces like the hood, doors, and bumpers to prevent damage during transport. The vehicle is then driven to the shipping yard where it is scanned, parked, and queued for delivery via truck, rail, or ship, depending on its final destination. The birth of a Honda automobile is not an accidental fusion of metal, glass, rubber, and electronics. It is the physical realization of a manufacturing philosophy rooted in discipline, simplicity, and human respect. At the core of Honda's automotive production process is the concept of monozukuri, a Japanese term meaning making things with craftsmanship and pride. For Honda, monozukuri is not just about building cars. It's about building trust in every nut and bolt, in every weld seam, in every panel gap. To witness a Honda car being built is to enter a tightly orchestrated environment where technological sophistication meets manual precision. Inside one of Honda's production facilities, such as the plant in Marysville, Ohio, or the Sayama factory in Japan, the scale is staggering. These plants are sprawling ecosystems of autonomous vehicles, robotic cells, and human operators working side by side across multiple production halls. And yet, despite their size and complexity, the rhythm of the process remains surprisingly calm. Everything flows according to plan, governed by Honda's unique lean manufacturing philosophy known as the Honda Production System. The journey of a Honda car begins long before any metal is cut. It starts with production planning, a phase driven by market forecasts, dealer input, supply chain readiness, and model demand. Honda's plants operate on a build-to-order basis more than most automakers. That means production schedules are crafted based on actual customer orders and real-time market demand. This approach minimizes inventory waste and maximizes the efficiency of the supply chain. Once the schedule is locked in, suppliers across the globe begin preparing the thousands of components that will soon converge at the plant. Raw materials like steel and aluminum arrive at the factory in massive coils. These materials first enter the stamping department, a cavernous space filled with towering hydraulic presses. Each press is fed with sheet metal, and fitted with enormous dies. Complex mold tools, shaped to form specific vehicle panels, such as hoods, doors, roofs, and fenders. The dies are interchanged automatically using massive overhead cranes and quick change systems, allowing the factory to shift between different vehicle models with incredible speed. These presses apply thousands of tons of force in milliseconds, transforming flat sheet metal into high-precision components with reinforced curves and load-bearing geometries. Each stamped panel is checked using template gauges or laser measuring arms to verify its accuracy against design tolerances. Honda's emphasis on dimensional precision at this early stage ensures that all panels fit perfectly during final assembly, which in turn improves both structural integrity and noise insulation. The stamped panels next travel to the welding shop, where the vehicle's skeleton, known as the body in white, is assembled. This stage is a symphony of automation. Dozens of robotic arms arc and swivel across each cell, welding panels together with pinpoint accuracy. These arms are fitted with spot weld guns, seam welders, laser cutting tools, and even rivet actuators, all pre-programmed for the vehicle model and trim level currently on the line. Guided by 3D coordinates, these robots can perform hundreds of welds in just a few minutes. Despite this high degree of automation, human workers play a vital role. Technicians monitor robotic operations, inspect weld seams visually, and perform manual welding in areas where robots cannot easily reach, such as complex internal joints or tight cavities. Importantly, Honda applies its stop-the-line authority in this department. Any associate who detects an issue is empowered to halt the line and initiate corrective measures immediately. This is part of Honda's respect for humanity approach, trusting operators not just to follow instructions, but to contribute actively to product quality. Once the weld shop produces a complete body shell, it enters the sealing and corrosion protection area. At this stage, structural adhesives and sound dampening materials are applied to critical areas of the body, such as the floor pan, roof seams, and door frames. These materials increase rigidity, improve crash performance, and reduce road noise. Seams are also sealed with flexible gaskets to protect against water ingress. After sealing, the body is conveyed to the paint shop, one of the most technologically advanced sections of the plant. Before any color is applied, the car is submerged in a series of cleaning and surface preparation baths. These include alkaline washes, acid baths, and a crucial e-coating step, in which the entire body is dipped in an electrically charged primer solution. The electrical current causes corrosion-resistant particles in the bath to bond uniformly with the metal, even in hard-to-reach crevices and weld joints. Once the e-coat is cured in an oven, the body enters a clean room environment for the color painting process. Robotic arms with electrostatic spray guns apply the primer, base coat, and clear coat in successive layers. Each layer is air-dried or heat-cured to ensure optimal adhesion and durability. Honda's paint robots use feedback-controlled nozzles that adjust spray patterns dynamically based on body shape and angle, reducing overspray and minimizing environmental impact. Between layers, the vehicle is visually inspected under specialized lighting conditions. Technicians look for drips, dust contamination, and color uniformity. If any issues are found, the body is flagged for manual repair, which may include sanding, buffing, or repainting a specific panel. Once painting is complete and the final clear coat has cured, the body is ready for general assembly, the stage where it transforms from a painted shell into a fully functioning automobile. Before reaching the general assembly line, however, many key sub-assemblies are built in parallel feeder lines located throughout the plant. These include engine and transmission modules, suspension components, dashboards, interior trim sets, seat assemblies, and wiring harnesses. Honda practices a synchronized sub-assembly strategy. Each of these components is produced and sequenced in real time to meet the exact build order of the cars progressing down the main assembly line. That means if car number 287 is a Honda Accord hybrid in touring trim, every part of that specific configuration is queued and ready to install by the time the body reaches the relevant station. When the painted body reaches the main assembly line, it is mounted onto a moving conveyor system. This conveyor will carry the vehicle through dozens of stations, each performing a specific set of installations or tests. The first few stations focus on interior preparation. Sound deadening mats are applied to the floor. Wiring harnesses are routed through the firewall and chassis, and the dashboard is bolted into place. Honda uses pre-assembled dashboard modules, which include the instrument cluster, HVAC system, infotainment screen, and most switches, all pre-tested before installation. This reduces line complexity and improves consistency. Seats, carpeting, door panels, and airbags follow shortly after. At every step, workers use a system of digital instructions, torque control tools, and pick-to-light part bins to ensure that the right part is used and installed to the correct specification. Honda's goal is zero deviation from build order, even in mixed model lines, producing different trims every few minutes. As interior installation continues, the process becomes more intricate. With the dashboard now secured, the vehicle receives its electrical control units, sensors, and remaining interior electronics. These are connected to the pre-installed wiring harnesses using color-coded, click-locked connectors that help eliminate the possibility of human error. Specialized quality control stations may test critical modules immediately after connection, especially airbag sensors and crash detection systems, to ensure they are responsive and correctly integrated into the vehicle's network of ECUs. Following this, attention turns to glazing and weather sealing. Robots or trained technicians carefully install front and rear windshields, applying adhesive in a uniform bead to ensure a perfect seal. The installation is timed precisely as the adhesive cures rapidly. Door windows, quarter glass, and side mirrors are added next, with their mechanisms tested on the spot to ensure smooth operation. Throughout this process, jigs and fixtures are used to maintain tight tolerances between the panels and glass, ensuring aerodynamic integrity, road noise insulation, and weather protection. The vehicle then reaches one of the most pivotal points in the production process, the powertrain marriage. As the body travels down the assembly line, a pre-assembled drivetrain module consisting of the engine, transmission, front or all-wheel drive differential, and suspension subframe arrives underneath on a separate conveyor. The marriage station uses synchronized hoists and laser-guided platforms to lift the body and lower it gently onto the drivetrain assembly. Once aligned, operators bolt the body to the subframe using hydraulic torque tools, which log each torque application in real time for quality traceability. The process of mating the body to the chassis and powertrain is more than a mechanical operation. It's an integration of identity. From this moment, the car ceases to be a shell and becomes a functional vehicle. After the marriage, systems are connected. The fuel lines, brake lines, wiring looms for sensors and control modules. Axles are bolted in. Radiators and intercoolers, along with their coolant hoses, are fitted. Exhaust systems are clamped into place and routed along the underbody using guides to prevent rattle or contact with heat-sensitive zones. Next come brake systems and suspension components. Brake calipers and discs are attached at each corner, followed by routing and fastening of hydraulic lines. ABS sensors and wheel speed sensors are snapped into their mounts, and their cables are clipped securely to avoid movement. Meanwhile, shock absorbers, coil springs or struts are fastened to the body using calibrated robotic arms or torque-controlled tools operated by line workers. These fasteners are critical as they influence ride quality, safety, and steering behavior. The wheels and tires, pre-mounted and balanced in a separate line, are then delivered just in time to the vehicle. They are aligned to the hub assemblies and fastened using pneumatically powered tools equipped with digital torque sensors. Each wheel torque is logged and checked against specifications. Even minor deviations trigger alerts. For instance, over-tightening a lug nut can damage threads or warp brake rotors, so precision is not optional. By this stage, the vehicle is mechanically complete, but not yet operational. It now passes into a startup and calibration zone, where the first true interaction between systems begins. Trained technicians perform a key-on sequence where all electronic systems are activated. This step includes powering up the main vehicle bus, initializing communication between ECUs, and performing a cold test of lighting systems, instrument clusters, wipers, and cabin electronics. The technician uses a diagnostic console to verify proper communication between modules and applies any last-minute software updates if required. Once the vehicle's systems are verified and error-free, the engine is started for the first time. A moment that is both mechanical and symbolic. As the engine cranks and catches, onboard diagnostics immediately monitor oil pressure, exhaust emissions, idle speed, coolant flow, and electrical charging. If any of these parameters fall outside of the calibrated range, the system flags the vehicle for further inspection. For hybrid models, the electric drive system may initiate instead, with the gasoline engine starting only after the battery's state of charge reaches a specific threshold. After the successful start, the car enters the rolling road test or chassis dynamometer. Here, it is strapped to large rollers that simulate road conditions. The car is driven through a standard cycle of acceleration, braking, shifting, and cruising, all while remaining stationary. This test evaluates key systems, including ABS, traction control, throttle response, gear engagement, hybrid transitions, and engine tuning. Sophisticated sensors and computers monitor hundreds of data points per second, ensuring the vehicle performs exactly as designed. Following the rolling test, the vehicle undergoes a headlight alignment and safety calibration station. Here, laser-guided systems measure the alignment of headlamps, and adjustments are made to meet both manufacturer and regional regulations. Advanced driver assistance systems such as lane keeping assist, adaptive cruise control, and forward collision warning are also calibrated at this point. This is accomplished using visual targets placed at known distances and angles in front of the vehicle, allowing cameras and radar units to learn their field of vision relative to the car's center line. Once these tests are complete, the vehicle proceeds to the water leak test booth, a sealed chamber equipped with an array of high-pressure water jets. For several minutes, water is sprayed at every angle, above, below, and from the sides, mimicking hurricane-force rain. Technicians inspect the cabin interior afterward for leaks, particularly around window seals, sunroofs, and door frames. Any sign of moisture sends the vehicle to a sealing team for immediate remediation and retesting. The car now moves into the final inspection area, often referred to as the white light tunnel. This zone is illuminated by intense, color-corrected lighting systems that reveal even the smallest defects in paint, fitment, and alignment. A team of inspectors walks around each vehicle, using mirrors to check lower panels, feelers to check panel gaps, and gauges to measure surface flushness. They assess the finish of paint, the gloss consistency, the evenness of door gaps, and the snugness of interior trim. Particular attention is paid to areas around weld joints, door hinges, and tailgate edges where minor misalignments can occur. Each inspector has the authority to flag the vehicle for any observed issue, no matter how small. Flagged cars are moved to a rework area where expert technicians resolve any concern before the vehicle can be released. Rework stations are not viewed negatively. They exist to ensure that every vehicle that exits the factory is indistinguishable from one that passed cleanly through all stages. After final inspection, the vehicle is prepared for delivery. Protective plastic sheeting is applied to painted surfaces and interior areas prone to contact during transport. The car is then driven to a shipping lot, where it is scanned into inventory and parked according to destination. Vehicles headed for domestic markets are grouped by dealership region and loaded onto transport carriers, while those bound for international markets are routed toward ports and loaded onto ships. The Honda factory's job may seem finished here, but in truth, its responsibility continues well beyond the factory gates. Each car's production data, including every torque value, software version, fluid fill level, and test result, is linked to its unique vehicle identification number and stored securely in Honda's manufacturing cloud. If an issue ever arises in the field, Honda can trace it back to the exact moment and operator involved in the car's creation. To witness the making of a Ford vehicle is to observe the evolution of industrial craftsmanship, a living embodiment of the assembly line system first pioneered by Henry Ford over a century ago, and refined today into a symphony of automation, digital intelligence, and human engineering. In modern Ford factories, like the Rouge Complex in Dearborn, Michigan, or the Oakville Assembly Plant in Ontario, production isn't simply about building cars. It's about orchestrating a precisely timed flow of materials, people, and machines that together transform raw components into advanced, drivable technology. The process begins long before the first bolt is turned or the first panel is stamped. The foundation of Ford's modern production system lies in rigorous planning and global coordination. Ford operates with a just-in-time and just-in-sequence supply chain strategy, meaning that materials and components arrive at the factory floor moments before they are needed. This eliminates the need for large stockpiles of inventory and increases the plant's flexibility to respond to changes in production schedules or model configurations. Planning starts with demand forecasting and order management. Using a centralized production planning system, Ford determines what models, trims, colors, and drivetrain variants will be built on any given day based on global dealer orders, regional demand patterns, and parts availability. This build mix is then converted into a master schedule that guides every action in the plant, from how robots are programmed, to which parts are loaded into which bins on which carts. At the heart of every Ford plant lies the stamping facility, where large rolls of sheet metal, primarily steel and aluminum, are cut and formed into individual body panels. These sheets arrive from external suppliers and are checked for thickness, flatness, and coating quality before entering the production line. Inside the stamping area, massive hydraulic or mechanical presses, sometimes up to 30 feet tall, use high tonnage force to shape the sheets into components such as hoods, roof panels, fenders, doors, and floor pans. Each stamping press contains tool and die sets, which are the sculpted steel molds that give shape to the metal. Changing these dies can take several hours on older systems, but Ford's modern plants use quick change tooling and automated die swapping cranes, allowing multiple model variants to be stamped in a single shift. Once stamped, each panel is inspected using automated vision systems and tactile measuring tools to ensure dimensional accuracy and surface quality. These stamped parts are then sent via conveyor or robotic shuttle to the next critical phase: body construction. In the body shop, robots dominate the floor. Here, the car's skeletal structure, called the body in white, is assembled from stamped panels. Using a combination of spot welding, MIG welding, and adhesive bonding, robots join together hundreds of individual panels to form a rigid structure that meets crash and durability standards. Each robotic cell is carefully synchronized, with arms moving in mirrored patterns to weld seams, attach reinforcements, and secure structural elements like the rocker panels and cross members. The entire body structure is periodically scanned with laser measurement systems. These 3D scanners create digital models of the assembled body to verify that it remains within tight tolerances. Even the smallest variation, fractions of a millimeter, could cause issues with later stages, such as door alignment or windshield fitting. If a body is found out of spec, it is automatically flagged and removed from the line for correction or further inspection. While the robots do the bulk of welding, human operators in the body shop play crucial roles. Some welds require access to tight spaces that robots can't easily reach. In addition, skilled technicians perform tactile inspections, feeling for uneven surfaces, sharp edges, or anomalies that a vision system might miss. They are also empowered to stop the line using an end-on system, a visible alert mechanism that signals an issue requiring immediate attention, a practice inherited from lean manufacturing disciplines. Once the body is complete, it's sent to the paint shop, a sealed and environmentally controlled environment that is perhaps the most intricate and sensitive area of the plant. But before paint can be applied, the body must be cleaned, prepped, and protected. It first enters an electrodeposition tank, or e-coat bath, where it is submerged in a liquid anti-corrosion primer. An electric current causes this primer to bond uniformly to every surface of the body, inside and out, including hidden cavities where rust could otherwise form over time. After curing in an oven, the body moves into a multi-stage painting process. Robots apply layers of primer, color, and clear coat using electrostatic spray guns, which attract paint particles to the metal surface like a magnet. The advantage of this method is increased efficiency and reduced overspray, leading to lower paint consumption and a cleaner environment. Ford's paint booths are equipped with air filtration and humidity control systems to eliminate dust or contaminants that could mar the finish. At each stage, lighting conditions are precisely calibrated to reveal imperfections, and technicians are stationed throughout the booth to perform quality checks. If a blemish is detected, a run in the paint, an uneven finish, or a missed spot, the vehicle is diverted to a paint repair zone, where the affected area is wet sanded, resprayed, or polished by hand to meet Ford's appearance standards. After the final coat, the body undergoes a final curing process in a high-temperature oven to harden the paint and create a durable, glossy finish. The now fully painted vehicle shell, known as the trimmed body, advances to the general assembly line. This is the most labor-intensive section of the factory, where machines and humans collaborate closely. Unlike the body shop, where robots dominate, the general assembly area relies more heavily on human hands, precision tools, and ergonomic aids. The car body is mounted on a moving conveyor system known as a skillet line or friction drive platform, which carries the car through a series of workstations at a constant, carefully controlled speed. Assembly begins from the inside out. First, teams install insulation pads and sound deadening materials. Next, wiring harnesses, which form the car's electrical nervous system, are laid out and clipped into position along the floor, firewall, and side panels. Each harness contains dozens of connectors that will link to ECUs, lighting elements, climate controls, sensors, and powertrain systems. Proper routing and fastening of these cables are essential for both performance and safety, so visual checks and scanner-based validations are used at multiple points. Then comes the dashboard module, which is typically pre-assembled in a nearby subline. It includes the steering column, HVAC ducts, infotainment screen, and instrument cluster. This large component is inserted into the cabin as a unit using mechanical arms and then bolted into place. Seats, carpeting, interior trim panels, seatbelt retractors, airbags, and roof liners follow, each added in a precise order, with visual and tactile inspections performed continuously to ensure flawless fit and finish. Throughout this interior build process, Ford uses error-proofing tools such as torque-controlled wrenches, pick-to-light bins, and vision-guided assist arms. Every torque application is digitally logged. If a bolt is over or under-torqued, the system automatically halts the line and flags the issue. This traceability is vital, not only for quality assurance, but also for future diagnostics should the vehicle need service or become subject to a recall. Continuing from the general assembly line, the next transformative step in the creation of a Ford vehicle is the marriage of the painted body with the powertrain and chassis systems, a defining moment in every car's life on the line. As the body shell makes its way along the conveyor, the fully assembled engine, transmission, suspension, and front subframe approach from a lower parallel track. These components, built and tested in a separate sub-assembly area, are synchronized to arrive at the exact moment when the body reaches the marriage station. Here, specialized lifting systems raise the powertrain module from below while the body is gently lowered from above. Technicians, supported by robotic arms and torque-controlled tools, fasten the body to the chassis at critical mounting points. This precise alignment is essential. It determines the geometry of the suspension, the drivetrain angles, and even the behavior of noise and vibration through the cabin. Fuel lines, coolant hoses, drive shafts, brake lines, and wiring harnesses are then connected between body and chassis, integrating the mechanical and electrical systems into a unified vehicle. After the marriage, the vehicle receives its cooling system, air intake, and exhaust components, followed by fluids, including engine oil, brake fluid, transmission fluid, and coolant, all filled using automated dispensers that monitor volume, pressure, and flow rate. These filling stations ensure consistency down to the milliliter, and if there is any deviation from the programmed values, the system stops the process and flags the vehicle for investigation. With the engine installed and fluids topped off, the vehicle is now nearly complete. It receives its wheels and tires, which are pre-mounted, balanced, and matched to the specific trim and model variant. These are installed using torque monitoring impact wrenches, and the system logs each wheel's torque values in the vehicle's digital build record. Exterior components such as bumpers, lights, badges, grille assemblies, and mirrors are now added, bringing the vehicle's final form into view. At this stage, the car has all its physical components, but it still needs to come to life. The next section of the line is dedicated to initial startup and systems calibration. A technician connects the vehicle to a diagnostic console and performs the first ignition sequence. This process powers up the ECUs, activates safety systems, and starts the engine. Immediately, a flood of data is captured: oil pressure, engine RPM, voltage, emissions readiness, and more. The technician watches for warning lights, verifies software synchronization, and confirms that all onboard systems are responsive. If all readings are within specification, the vehicle advances to functional testing, where every major system, lights, brakes, steering, wipers, infotainment, HVAC, and electronic safety aids, is tested in a rapid, choreographed routine. Ford technicians use handheld devices and sensor panels to trigger functions and confirm their proper operation, all while the vehicle moves slowly along the inspection path. Any anomaly here diverts the vehicle to a diagnostics bay for further analysis.